All right, good morning, everyone. Can we all hear me okay? Yes. All right, well, I'm really excited to be here. I hope you're really excited to be here. I think we're going to learn a lot today, and so let's just get straight into things. So I am Ethan Niser. You've probably seen a couple of my YouTube videos before. I've made some about effect. I made some about this stack called the Beth stack. I made this npm package called typesafe URL. And full-time, I am actually a high school student. So missing class right now, but I think I'd much rather be here. So I first found out about effect around a year ago, and I think I was just really blown away right from the start. Um, and the reason for that is I think the big thing to understand about effect is that it makes our programs easier to understand. So when you go to the website, right, on the homepage, you'll see all these words. You'll see like safer, more composable, more observable, and those are all really, really true. But I think, again, the core of it is that effect is a framework that makes our programs easier to understand. So today, what are we going to do? We're going to start with an introduction to effect's core concepts. So I know some of you may have worked with effect before. Some of us are beginners. And so we're going to start out all the way from the beginning and go over from the very first kind of core concepts and kind of build our way up. And so then we're going to move into some real-world examples. We're going to rewrite two different applications that are not in effect, and we're going to slowly, kind of incrementally rewrite them to effect. And then we're going to end off the day with a peek into advanced effect. And so these are just kind of some more advanced topics that you might be a little scared to try out on your own. And so we're just going to kind of show you a little bit of that. And the one thing I want to stress today is that there's a lot of room for elasticity in the schedule. So if the kind of first section takes longer than the kind of first 90 minutes we have blocked out, that's totally okay. If we don't end up getting to everything, that's totally okay. I promise you will learn a lot. And so if we run out of stuff to talk about, there's plenty of stuff to talk about. But in the much more kind of likely scenario where things are going a little bit slower, it's totally fine if we don't get to everything. All right. So what do you need for today? So there's a Git repo. It's on my GitHub. And so this is not actually required. You could just pay attention. But if you want to follow along, there's a lot of exercises we're going to do. Obviously, the apps we're going to rewrite, you can follow along on your own. And so if you want to run it locally, you can clone it. But if you want to open it in a GitHub code space, that's also a really easy option. And then the other thing you're going to need is just some way to run TypeScript. So I'm going to be using Bun just because it's a lot faster to run files. But if you are using Node, that's totally okay. If you have TS Node or TSX, both of those are going to work just fine. Just you need some way to run TypeScript. And then if you are opening in a GitHub code space, I made this little start.sh file, and all this does is install Bun and runs Bun install. So it's very, very simple. If you are having trouble kind of getting the repo set up, please let me know. And so while you're doing that, I'm just going to kind of keep talking while you set that up. So the one thing that I also want to really stress today is to do your best to not feel overwhelmed. I know some of you, again, have worked with effect before. Some of us are brand new. Effect can be really overwhelming. There's a lot going on. I don't know how many of you have looked at the API reference page before. There's like 30 modules. You go into each module, there's like 200 functions. And that can be really overwhelming. And so what I want to stress is that the learning curve is actually quite gentle. There's a lot of modules and functions that you could go years and basically never touch. And so today we're going to start off with kind of the most common and most basic things to understand. And so here's a graph I made. And it basically, on the top we have, or on the y-axis we have usage frequency, and on the x-axis we have complexity. And so this is kind of how a lot of the functions and modules in effect are kind of used, right? Where the most common things are used all the time. And as you kind of get more and more obscure, there's going to be a lot of functions that are very advanced, very low level, that you might never use. And so we're going to spend most of our time today, if I pull up here, we're going to spend most of our time today like here in this area. And then the last section, we're going to look a little bit here. And so again, don't feel overwhelmed if you kind of go to the API reference page and you see some of this stuff and you're like, wow, that seems like a lot. Right? And then the other thing is interactivity today. I really don't want to be up here talking for 5.5 hours, so please, please, please ask questions. I've planned in some spots. We're going to have kind of review problems and exercises, and I'm going to be asking for questions a lot, but I want to make sure everyone kind of feels comfortable prompting interaction as well. And then we also have some other kind of effect people in the room. I know Tim is here. Some other people might come in and out. And so if we have like maybe some more advanced questions or questions that kind of go off topic, they can be there to help out and answer those. But I would say most of the stuff I can definitely handle. And with that said, is everyone kind of good setting up the repo? No one's having trouble? All right. So the first thing that we're going to talk about is what is an effect, right? This is a pretty core concept. And so what is an effect, right? There's kind of this formal definition. So something brought about by a cause or an agent, right? So we have cause and effect. And then, we're programmers, right? We have these things called side effects. Our programs kind of have effects on the outside world. We know that kind of, some functional language try to like capture side effects. How do we structure them in our programs? And then, of course, in effect, we have this thing called the effect type. And so the effect type is a thing in effect that is really the core of the kind of entire effect framework. And so if you go to the website, the effect, it says an effect is a description of a program that is lazy and immutable. Okay, so the kind of three words that stand out to me there are program, lazy, and immutable. So what is a program? Well, I would say a program is kind of a series of steps, right? And so maybe we could say a short JavaScript script, right? Like I would describe this as a very basic program. And we can run this program. Of course, I forgot to mention, so in the GitHub repo, there's a README. You might have checked it out. The main thing in the repo here is there are scripts to run each file. So the way the repo is organized is there's a folder for each of the parts. And then within each parts, there's some folders. There's some exercises. There's some snippets. In the middle two parts, there's a project and a breakpoints folder. And to run each file in package.json, there's a bunch of scripts I've laid out. And so if you are not using bun, you can just find and replace bun run with like npx tsx if you're using tsx. And so the pattern is basically the number of the part, the first letter of the folder, and then the number of the file. So I'm about to run this first kind of what is a program.js file. And so to run that, I'd run 1s1. And so that's going to be the pattern for most of the files. So you could obviously run it just by typing out the full path, but some of the paths can get a bit long. And so when we run this, obviously, we kind of get the expected output. And so one of the other things about this program, right, is it's kind of inherently lazy, right? Like there's nothing that happens on our computer until we kind of pass this program to bun or node. And then even within our program, right, like if we throw an error halfway through and we run it again, the final console log never goes off. And so that's where we kind of start to get into this second aspect of laziness, where we delay work until it's needed, right? So in this script, our computer doesn't calculate this kind of second square root. It doesn't do this log. And so the final thing that I mentioned is immutability, right? And so scripts are kind of inherently immutable, right? Like we can mutate our script by editing it, but after we give it to node, after we give it to bun, our source code is not being mutated in real time, right? So that's kind of those three concepts of immutability, laziness, and a program. Now, obviously, we've looked at like a JavaScript script, but the effect has this. An effect has all three of these properties, but an effect is an in-memory type, right? So it's something inside JavaScript. So what is something that is not an effect, but is also kind of inside JavaScript that has all three of these properties? So a program, lazy, and immutable. Anyone? So I would say a function, right? So a function is something that exists within JavaScript, and a function it's a description of a program, right? Like, so we have this function foo, and this function kind of describes some behavior. So it's a description of a program. It's also lazy because if we run this script, right, nothing happens even though we've declared the function, right? Functions are lazy until we call them, right? Only when we call a function, that's when we're kind of executing that behavior we've described. And then finally, we have immutability, right? Like we can't mutate what this function does after we've declared it. We can reassign that variable name, but there's really no way to mutate the body of a function. And so that's where effects come in, right? Effects are not functions, but they kind of have all three of these properties, but they build on top of what functions are able to offer. So now we're going to move on to kind of what effects are able to So now we're going to move on to what effects kind of offer on top of functions, right? Like obviously we use functions all the time. What can effects kind of bring us that function stuff? And so the first is this kind of type, right? And this describes basically most functions. We have some type of arguments and some return type. And if you've watched some of my videos before, you know that the problem with this function is it doesn't really prescribe an error type within it, right? And so a lot of our behavior within our programs can error, and we kind of want to encode that error in the types of our programs. But by default, obviously, with try-catch, when we throw something, we don't really know what error kind of is getting thrown. And so we can create safer functions that return unions of either whatever type they're returning or some kind of error. But there's still some problems with this. And so the first problem with this is that it can become kind of hard to discriminate the error. So in this first example, we use instance of to discriminate the error. In the second example, we use kind of strict equals. And so obviously, another kind of solution that you can use instead is tagged errors. But even then, we kind of get into this next problem of composing functions that error. And so this is a pattern you'll see a lot in code that kind of has these union error types, where we have an inner function that might error and an outer function that also might error. And we want to kind of only operate on the value if it's not an error, and otherwise kind of continue that error. And so in this code, we get the result, and then we have to manually check if it's an error, and then if so, we return the error, and otherwise we can work on the result. And so this is kind of a limitation of functions that can return a union, because you have to kind of manually check. And so this is something that, right, we are forced to handle errors at every point, even if we don't necessarily care about the error. And so effects are different. So the first way effects are different are they have a error type parameter. So an effect, right, here's kind of what the effect type looks like. And the effect has two type parameters. So we have a value and an error. And the error is by default never. And what that means is that that effect can never error. And so this first example, we have foo. And foo is an effect never, or number never, which is the same as an effect number, because again, the second type parameter is by default never. And so this describes an effect that can either succeed with a number, and it will never fail. Like, there's no possible way for it to fail. And this next example, this bar, is an effect that may succeed with a number, and otherwise it may fail with an error type, like the error class. And so what this does is, and we'll go through how you kind of build on top of this, but by having errors as kind of first class citizens, right, we are encoding the types of our errors all throughout our programs, right? So we can describe effects that have errors and what types those errors actually are. And then the kind of error composition problem I talked about, effects have a really cool way of solving that, which we'll get to in a bit. So, and for the people coming in late, I'm glad you're here. The one thing I want to make sure that you are able to be with us is there is a Git repo. So it's on my GitHub. It's called Effect Workshop. And so you can clone it. And all you need is some way to run TypeScript. So either Node with TSX or Bun, whatever works. I'm going to be using Bun. And if you have that, you're pretty much good to go. And so the next thing that we kind of gain on top of functions when using effects is dependencies. So here's an example where we have a function that kind of has this implicit dependency on this database import. And it would be ideal if we could kind of provide that dependency explicitly. And so that would look like kind of passing it in as a function parameter. And the benefits we get from this are we can kind of mock the service or the kind of database much easier, right? So if we're testing this function, we can provide either a real database or we can provide an in-memory database. It really doesn't matter as long as it conforms to this database interface that we provide. And so this is something that is kind of beneficial in our code. And the problem is a lot of the times it's really kind of obtuse to pass things in by function parameter like this. And so a lot of the times we just end up importing it. And the reason for that is while this example is pretty simple, a lot of the time our code ends up looking like this, right? We have a database and we have a logger and we have telemetry and we have a number of other things that we need that we're all passing into our functions. And this can get kind of a lot, right? Like we now have more parameters that are really not about the logic of a function than the actual what the function is doing. And so this leads into the third type parameter that an effect has. So it has the value type parameter, it has the error type parameter, and it has this third requirements type parameter. And what the requirements type parameter describes is the types of the services that effects requires. So as an example, this function requires a database and a logger and a telemetry. And so here we have an effect, and this effect is called getUser. And this getUser is an effect that will succeed with a user value. It will fail with a not found error value, and it requires a database. And so what this is saying is that this effect uses a database of this database type somewhere within it, but it doesn't yet have an implementation. And so then the reason this is important is because on a type level, we can say that we shouldn't be able to kind of execute any effects where this third type parameter is not never, right? Because if it's not never, it's saying, well, we depend on some type, some service that we don't have. And so in that way, we can track these dependencies throughout our program. And so this next example, we have a update email effect. And so this is going to similarly kind of return a user, or it's going to have a not found error. But this one requires multiple services. So it's going to require either, or not either. So the one kind of thing with services is they're encoded as a union, but that's, and the reason for that is it's a bit complex, but you need all of them. So this is saying that this effect requires a database and a logger and telemetry. And so only when the effect has a third type parameter, this requirement type parameter of never, is when it's safe to execute. And so we can see that where this is just some pseudocode, but we have this provide dependencies function. And so if we provide dependencies to this getUser effect up here, we can see that now we can provide the database to that effect, and now the third type parameter is never. And also, we can provide a kind of mock DB, right? As long as it also conforms to this database service, both of these are going to end up as never. The next thing that effects kind of provide to us over functions is they abstract away sync versus async. So obviously with functions, we have asynchronous functions, we have synchronous functions, and you kind of run into this function coloring problem, as it's called, where you can only call asynchronous functions from asynchronous functions, and as soon as you have one asynchronous function, everything kind of becomes async. And so effects abstract this away. So there is no async effect, there is no sync effect, there is just the effect. And you might be wondering kind of how effect handles that difference, because it is an important difference. And we will talk about that in a bit, but just for now, you can understand that there is no sync effect, there is no async effect, there is just the effect. And then finally, we have execution. So as I kind of showed earlier, functions are just objects, right? They're just values. And so if we just log the value of a function, we just get that function. And we have to call the function before it actually does anything. And so effects are the same way, except we run them. So we have an effect, and if we log the effect, right, we just get this value. But if we run the effect, that's when the kind of contents of the effect get executed. And so there's a couple different ways to run effects. We'll talk about that in a bit. But again, just like you call a function, you run an effect. So now we're going to move on to creating effects, right? We need to kind of, this is like the lowest level kind of base how to get started, right? We have to create effects from nothing. And so we're going to go over 7 functions to create effects. And I know that sounds like a lot. In actuality, there's over 20. But like I said, don't get overwhelmed. A lot of these are kind of just kind of slightly different versions of other ones. And so like I said, we're just going to stick to 7. So I'm going to go into the creating effects file here, if you want to follow along. Is the text big enough for everyone? Yep, all right. So the first two functions we're going to look at are succeed and fail. And so these create effects from values, from just values. And so this is important because we talked about kind of laziness, right? Like functions are lazy, and effects are also lazy. And so when you evaluate a function, all of the function arguments get evaluated when you call the function. And so if we're creating a function from a value, it's important that that value is not like doing anything. It's just a value. So we have just a number 1 or just a string 2. And so the two kind of constructors to create things from values are succeed and fail. And so succeed here, we're calling effect.succeed1. And by the way, we're importing the effect module from effect at the top. And so effect.succeed1 is going to return an effect number never, never, right? And so, of course, you can write that just as effect number because those other two default to never. And so what this is saying is this is an effect that when we run it is going to return or kind of succeed with a number, and it can never fail, right? Because we haven't even given it a way to fail. It only can succeed. And so the opposite of that, of course, is fail. And so fail is going to fail with the value you pass it to. And so this is going to be an effect never string, right? Because this effect can never succeed, and it's going to fail with a string. And so as I talked about, you don't want to do anything that's a side effect or some kind of computation when you're using these value constructors. Because, so for example, if we create this effect.succeed date.now, this is going to return a number, but it's going to return the number of the date when we created the effect, not when we run the effect. And so this is equivalent to basically creating a variable that has now and then creating a function that just always returns that one value. And so if we want to do more than just create from values, then we have creating effects from synchronous computations. And so for that, we have effect.sync. And effect.sync takes what's called a thunk, which is basically a function that doesn't have any arguments. And it's going to return some value. And the value that it returns is going to be what this effect itself returns. So this effect is also an effect number, right? Because date.now returns a number. But what we're saying is when we execute this effect, only then we're going to run this function inside. And so that's going to get the kind of date when you run the effect instead of when we're evaluating the effect. And this is also where we can start to introduce side effects. So if we want to log to the console, we can put that inside the thunk of an effect.sync. And that way, we're only logging to the console when, again, we execute the effect. Now, something you'll also notice is if we throw an error, the effect that's returned is still a never in the error channel. And the reason for this is that effect.sync assumes that the function you pass to it will never throw. And this is an important assumption because a lot of the times functions you kind of can know they won't throw. But if this function throws, it's not going to be considered an error in effect. It's going to be considered a defect. And we'll talk a bit more about defects later. But a defect is basically like a panic or an uncaught exception, right, from other languages. And a defect is basically going to end your program, right? It's an unexpected error. But we don't want unexpected errors. We want expected errors, right? That's why we have that error type parameter in the first place, because we want to kind of see the errors coming throughout our programs. And so that's where we can start to introduce errors with try. And so effect.try is kind of a version of effect.sync that is going to now propagate any errors into the returned effect. So this is basically the same thing as up here, but we're using effect.try instead. And so effect.try is going to return an effect number or unknown exception. And so it's telling us here on a type level that, hey, this effect, you've told me it might error. And if it errors, it's going to return this unknown exception type. And the reason for that is we haven't kind of told it what kind of error is going to be thrown, right? Or what kind of error is going to come out of this effect. And so by default, when you catch something, you could catch anything, any type, right? When you catch, it's unknown. And so this is saying this is an unknown exception. But unknown exceptions are not very useful, right? Like this is almost no better than try catch because we don't really have any kind of useful information about this error. And so that's why most of the time when you use effect.try, you're going to use this overloaded version. And so this is the same thing as try, except instead of just passing the function, we're passing an object with a try function and a catch function. And so the try function is the function that we want to execute, and that's going to, and whatever this function returns is going to be the success type of the effect. So JSON.parse returns any, this effect is going to return any. But if this try function throws, then effect is going to move into your catch function. And so the catch function takes an unknown error, right? Because this is whatever is caught, and we have no clue what this value is. And then you're going to remap it to some kind of known error, right? And so then we can see that this effect now errors with an error type, because that's what we've told effect to kind of remap that error to. And so something else we could do is maybe we can create our own error type. We can call this JSON parse error. And instead of returning this error, we can return a new JSON parse error. And then that's what's going to be kind of in place in here. And so you can create your own error types and kind of, and in this case, you can obviously create a class with any values you want, any kind of data you want. But in this case, kind of having this distinct error type, even without like the message we had before, this might be enough to kind of know what happened, right? Because when we're processing these errors later, we can see, oh, well, this was a JSON parse error. It's not like some opaque error type that we have to look into its string message to get, right? So we're having typed errors, which is really powerful. So obviously, that was just synchronous stuff. So now we're going to move on to asynchronous computations. So for these next examples, we have this wait function as an example of something that returns a promise. So this function is going to take a number of milliseconds, and it's going to return a promise that resolves with a string after that time. And so we can create an effect from a function that returns a promise with effect.promise. So here we call effect.promise, and then we're calling wait within the function that we pass to it. And that's going to return a string never. And you'll notice that's not promise string, right? Because effect is handling all of the asynchronous stuff for us. It's just saying, you gave me a promise string, here is an effect string. And so just like try, promise is going to assume that this function you pass to it, that this function is not going to throw, and the promise returned from it is not going to reject. And so just like there's try promise. And so try promise also has a kind of unoverloaded version with an unknown exception, or a overloaded version where we can remap the error to a kind of known useful error type. And then if you're not necessarily working with promises, if you're working with kind of callback-based APIs, there's effect.async. And effect.async is going to give you this resume callback that we can either pass a effect failure to or an effect success to. And so here we're using read file from Node.fs, which takes a callback with either our error or our data. And so if it's an error, we're going to fail with the error. And if it's a success, or if it's not an error, we're going to succeed with the data. And then all these other examples so far, we've all been inferring the types. But this last example, you'll notice we do have to manually type these. And the reason for that is that it's just a limitation of TypeScript, that it can't infer the types for this outer function from how the callback is used internally. So in order to kind of use effect.async, you do have to define the success type and the error type. To recap, right, we have succeed and fail for values. We have sync and try for synchronous functions, promise and try promise for async functions, and async for callbacks. And then, of course, if your functions have any chance to error or your promises have any chance to reject, you're going to want to use try or try promise so that those errors are kind of known typed errors and not defects. Any questions so far on what we just looked at? Cool. All right, so next we have running effects, right? We've kind of created these effects, but they don't do anything right now. They're not that useful. They're just values. And so I talked about, just like we call a function, we run an effect. So we have a couple ways to do that. And so for this kind of snippet, we're going to have these three example programs. So the first program is a program that's going to succeed. It's going to it's going to log to the console, and then it's going to return a number. So this program is effect number never never. And here we have a program that's always going to fail. right? It's going to return either a number or an unknown exception, but really it's always going to kind of fail with that unknown exception because we're throwing. And then finally, we have a program that's internally asynchronous, right? Again, effect is not kind of, you can't tell whether it's sync or async from the outside, but we know that this program is asynchronous from the inside because we're using effect.promise. And so if we kind of log these out, and this is going to be 1s5, we kind of get these values. And these are kind of interesting to start kind of looking at how effects kind of work under the hood, right? So this kind of synchronous effect, basically what it is just this object that has the function that we gave it inside. But you really never need to worry about the internals of the effect, right? We're just kind of thinking of them as kind of opaque. We really only care about the type, right? And so to run effects that are purely synchronous, we can use the run sync function. So we pass our successful program to run sync, and it's going to synchronously return whatever the success type of that effect was. So in this case, a number. And so we can log that out. So if we run this again, right, we're going to get the console log and the result being 42. And so run sync, if the effect kind of that we pass to it, if the effect fails, it's going to throw an error with whatever the type of the failure type of that effect. So this effect could throw with an unknown exception, and when we run it, you can see that we get this unknown exception thrown out. And then finally, the reason it's able to return the effect synchronously is because it will only execute effects that are purely synchronous internally, right? Even though, and so this is obviously you're not able to tell from the outside, so we don't get a type error when we call run sync on this async effect. But when we try to run it, we're going to get this kind of cryptic error. It's going to say run sync, async error cannot be resolved synchronously, caused using run sync on an effect that performs async work. And so what's happening under the hood here is, again, although externally the effect we can't tell, internally that kind of async effect is kind of async instead of sync. And so when we call run sync, it's basically as it's executing the effects, it's saying if there's an async effect, well, I don't know how to execute this because I can only return synchronously, so I'm going to kind of throw this error. And so if you have any part of your program, even like one effect that basically uses promise or try promise or anything async, you're going to need to use run promise instead. And so this ends up being what you use for the vast majority of programs because it's kind of very rare that you're doing anything effect that's not async in at least some capacity. And so if we pass our program to run promise, we're going to get a promise that resolves with the value type of the promise. So in this case, we have our async program whose value type is number, and so run promise is going to return a promise of a number. And so we can call .then and get the result. And then also, if we pass the failed program, that promise is going to reject with the type of the error type of the failed program. So if we run these, right, we get the run promise result, and we get this error, which is catching the failed program. And then finally, there's this function called run sync exit, and there's also run promise exit. And run sync exit is going to return a exit type. And we'll talk a bit more about this in a second. But you can basically think of it as, instead of just throwing the error, we can get this exit type, which is basically a union between either the success or the error. And so then we can kind of discriminate on that exit type, which is a lot of the times much more kind of useful than just throwing the error, and then we're kind of back into try-catch land, right? So if we log this one out, we log these, you'll see we get this exit, and this has a tag of a failure. And so again, we'll talk a bit more about exits in a bit, but just that there's other functions that kind of, instead of throwing or rejecting the values, right, we can get them as a union. All right. So far, oh, yes?
So this exit type is basically the same as the
It's similar. So we're in a couple, in like probably 20, 30 minutes, we'll kind of really look into the exit type. But you can basically think of it as an either. It's actually a bit more powerful than an either, and I promise we will talk about that in a bit. But you can kind of conceptually think of it as either the success or an error. Yes? Yes, yes, yes. And I do think we cover this a bit later, but a tag is, so the question, I'm sorry for not repeating it, is what is the kind of underscore tag field of a lot of the objects in effect? And so this is a very, very common pattern you'll see all over. And so a tag is a field to discriminate two things. And so the usefulness for this is on a type level and also on a runtime level. So on a type level, it's useful because TypeScript will merge two kind of items in a union if they're the exact same. So if we have like a, and we can show this. So if we have like type, we're going to call this 1, that's going to be foo string. And if we have type 2, it's going to be foo string. Let's capitalize this. So if we call this type union, and this is going to equal 1 or 2, you'll notice that this actually, if we, I guess it won't happen here, but there's kind of scenarios in TypeScript where unions will kind of get merged implicitly if if the objects are the exact same. And so what the tag does is the tag will basically say, it might be because I think if we make these, I'm sorry? Yeah. Oh, okay. Yes. So what he said for you guys was if you have certain kinds of classes in a union, they can get merged. And so what the tag looks like is we'll have this read-only tag field as 1 or, and so what this tells TypeScript is that these kind of objects are distinct types, right? Because even if the rest of the type is the same, that these are different because of this tag. And it also is important on a runtime level, because if we kind of declare a union, we can kind of switch on the union, right? And so then if we have based on the tag is a union of all the possible tags. And so when we kind of check manually to make sure that the tag is a specific value, we automatically know the type of the rest of the thing, assuming all the tags are unique, right? So a tag is a way to discriminate two types, both on a type level and both on a runtime level. Does that answer your question? Okay. So far our programs are quite limited. What we really want to do is kind of start to compose our effects. So right now we can only kind of create effects from values, we can create effects from functions, we can run them, but we really want to kind of build up our programs. And so this is an example of composing functions, right? So we have a getDate function and we have a double function, and then this double date function doubles the date, right? This is a very basic example, but we're kind of combining the behavior of two separate things. And so let's say we want to kind of combine the behavior of two effects, right? So we have getDate, which is an effect that kind of synchronously calculates the date, and we have a double function. The way to do it is definitely not this. You never want to run effects inside other effects. And we'll talk about a better way to do this in a second. But running effects inside other effects is like the one big no-no of effect. You basically throw away all the benefits of using effect if you run effects inside other effects. And so you should only run effects at the edges of your program. And what this means is kind of when you have to interact with something else. So if that's, if your program is entirely effect, then usually you can call run once, a single time, and that's going to run your entire program as an effect. But if you need to interact with kind of other code, right? So if you are using effect kind of interoperably with other libraries that don't use effect, that's when you have to call run, because you need to kind of convert the effect to the value, right? But running effect at the edges of your program. So what is a better way to do this? So we're going to answer that in a second, but the first thing we're going to talk about is pipelines. And so a lot of the times in our programs, we want to basically transform data through a series of functions. And so here we have an example. We have a function called getDate. We have a function called double. It's going to double a number. We have toString. It's going to call toString on the number. ToUpperCase. It's going to call toUpperCase on the number. And a lot of the times, really kind of how our programs end up is just as the kind of successive piping of data through one function into the next function, into the next function. And so we can kind of look at that like this, right? We can call getDate and call double on getDate and call toString on that, call toUpperCase. But this can be a little hard to read. You kind of have to read inside to out, and it can get pretty complex if you start having kind of other parameters baked in here, right? Like what is the function actually operating on? It can get a little complicated. And so there's some other kind of alternatives here, right? Like object-oriented programming. We can make classes, and we can use this kind of cool method syntax, right? And that way we can very clearly kind of read left to right. But this kind of loses a lot of problems, right? Or introduces some problems where, especially when we make things classes, if we want to kind of give those classes a lot of behavior, right? Like let's say we have a class with 100 methods, but we end up only using 2. Well, all those 100 methods, they have to be on the prototype of every kind of instance of that class. And so there's no real way to tree shake the kind of the methods of functions. And so that's why, or the methods of classes, sorry. And so that's why effect uses functions. And that's why we do this kind of, if you'll notice from before, right, we import effect, and then we call all these functions as kind of namespaced functions, or namespaced imports, right? Like this is not a method of some big effect class. This is a function from the effect module. And so we want to be able to get this kind of same really easy to read left to right composition without all the kind of drawbacks of throwing everything on a class. And so the solution to that is something called pipe. So pipe is a function that we can import from effect. And when we pipe things, we are basically giving it a value and a list of functions. And what you'll notice is that this example down here with pipe actually looks very, very similar to this method example, right? Like the functions kind of line up almost perfectly. And so we get the same readability of kind of getting our date and then doubling it and then calling toString and calling toUpperCase, but we do this in a much more functional and much more composable way. And so pipes are really, really core to effect because basically everything we're doing is functions. We're calling functions, passing them to other functions and other functions, and so it's really important to have pipes to be able to very neatly be able to call successive functions on our data. And so now we're going to go back to effect, knowing this kind of pipe, because we're going to be using pipes in a second. And again, we have this example, the bad example, calling run sync inside effect. And so we don't want to do this, but what can we do instead? Well, we can try this, right? We can try to pipe getDate into double. And this obviously isn't going to work, right? Because double takes a number, and this is an effect of a number, and those are kind of incompatible. So we need a way to kind of get in to that effect, like kind of operate on the value within the effect without running it. And so the way we do that is this function called map. And so what map is going to do is it's going to take an effect and a function that operates on the type of the value of that effect. So this function is a number, and then we can call double on that number, and the effect that's returned from map is going to be the result of whatever this map function returns. So instead we could call x.toString, right? And now this is an effect of a string. And so what this is doing is, again, these are our new values. Like this double date 3 is a new kind of separate immutable value from this previous getDate function. And so double date 3 is now a program that represents first kind of do whatever getDate says, and then if it succeeds, right, and we have the value, then apply this function to that value. Call this function with that value, and then that's going to be the new result of this effect. And so now we can recreate our program up here where we kind of call getDate and the double and toString and toUpperCase, and we can take our getDate effect and pipe it into effect.map with the double function, and pipe it into effect.map with the toString function, and then into the uppercase function, and we can create one effect that represents all of those operations combined. And we can run it. I think this will work. And that's going to be the doubled string. So something you might be wondering is up here, we use effect.map with two parameters, right? We pass the effect as the first argument and the function as the second argument. And this is a pretty common pattern where the thing that we're operating on is the first argument, and then kind of the subsequent things are kind of options to that function. But here, we only pass one argument, right? We only pass the function. And the reason for that is that effect.map and basically every other function in effect has two overloads. So these are called the data first and the data last version. And you really actually don't need to know the names because you'll almost never think about this, and everything just kind of works. And so if you want to call the function with the effect as the first argument, you can, and it just works. But if you want to use it in a pipeline, and you can just leave it out. And the reason for that is because if you leave out the first argument, this is actually going to return a function that takes an effect. And so what this is kind of doing internally, right, is it's calling the result of this with this, right? This is what that looks like. So we're calling the function that effect.map returns with getDate. And so that's how we're able to use these functions in pipe without having to do something like this, right? Like previous, and then we can call effect.map previous, and then, right? This is what we would have to do if that wasn't the case. We'd have to kind of every effect or every function that didn't have one argument, we'd have to kind of use this anonymous function. But because basically every single function in effect has this overload behavior, you can just leave out that first argument, and it's just going to kind of work really easily in pipelines. So the next thing we're going to do is map with this divide function. So this divide function is a function that returns an effect of a number or an error. And basically, first we check if the kind of thing we're dividing by is 0, and instead of kind of returning nan, right, we're going to return this error. And so what we really want to do is map with this divide function, right? So we succeed with a tuple, and then we're mapping with the contents of that tuple, and the thing we're mapping to is the result of dividing by that thing. And so if we look at the type of this program, it's an effect whose success value is itself an effect. And so this is kind of a problem, right? Like we really don't want to run the effect and then run the effect we get from that. And so what we really need is a way to kind of flatten those two effects. And so that's why we have this function called effect.flatMap. And so flatMap is basically the same as map, except it's used when the function that we're mapping against also returns an effect. So here, right, we succeed with this tuple, and then we map on the tuple, and we divide, and the result is going to be one single effect. And when we flatmap, the result of the kind of the resulting effect will have whatever value type this effect returns, right? So this effect returns a number, so this effect is going to succeed with a number, right, not return. And also, flatmap is going to combine the errors, right? So that's not in this example, but if this effect, right, if this effect had an error, then that error is still going to come through in the result of the flatmap, right? It's going to combine the errors, because if this first effect failed, then that failure is, right, we can only flatmap on the success result. So if the first effect fails, the kind of resulting effect of the flatmap will also fail. And if the effect returned by the flatmap, if that fails, right, the whole thing is also going to fail at that value. So this is going to succeed with the success type of this effect. It's going to error with the types of errors from both the first effect and the effect we're flat mapping against. And so an example I came up with to kind of help conceptually understand what's going on here is we have this bash command. We have ls piped into grep, and we can think of these kind of like effects, right? So ls is a program, right? If an effect is a program, ls is a program. that when we run it, kind of does something. And grep is its own program, right? Like grep takes some input, and it's its own thing. And so pipe is kind of like flat map, right? We can pipe ls into grep, and now this resulting string, right? This is now its own program that describes both of those behaviors. And so that was what flat map is basically doing. The next thing we're going to look at is kind of triggering side effects without kind of altering the value of our effect. So what I want to do, we have this pipeline, right? So again, we're synchronously calculating the date, and then we're mapping with some functions. And what I want to do is, in between, before we call toString, I want to log out the value here, right? I want to kind of inspect the value, if you will. And so the way I could do that is this, right? So we're adding in this map. And what this is going to do is it's going to kind of do our side effect. It's going to log the thing. And then we have to return x here. Because if we don't return x here, and we actually can just make this like one expression, right? If we do this, then we're going to get an error down here. Because now this is void, right? Because we're flat mapping against the result, or we're mapping, not flat mapping. We're mapping against the result of this. And console.log returns void. So now this returns an effect that succeeds with void. And so kind of returning the value through, right, so that this next map function still has the same value that we've been working on before. This is a little bit kind of annoying. And so that's why we have this function called tap. And so tap is basically map, except we are completely ignoring the result of whatever gets returned, right? We're just doing something. So we could call, right, like we could double x in here, but that's not going to impact x at all, right? And so this is where we can kind of do side effects on the result of our effect without changing the value itself. And so the final thing we're going to look at is how to combine effects. So we have effect.all. And what effect.all is going to do is it takes an array of effects and returns an array of their results. So we have this first effect that calculates the date. We have the second effect that calculates the date yesterday. And we go from an array of effects to an effect that has an array of two numbers. And so then, right, we can call effect.all, and then we can map on the value. And of course, now it's a tuple, and so we can kind of unpack that and combine those. And so another useful thing you can do with effect.all is instead of passing an array, you can pass an object, right? So we can pass an object where the values of the object are effects, and we're going to get back an object where the values are the results of those effects. The next thing we're going to look at is effect generators. So you might have seen effects generators before. They're probably like the thing that stands out the most about effect. And they're an alternative way to compose effects. So instead of using functions, we can use generators. And so to introduce generators, I have this pipeline. And so this pipeline, again, we're reusing this divide function from earlier, which again returns an effect of either a number or an error. And so we're synchronously getting the date, we're mapping it with a function that doubles, we're flat mapping with this divide function, and then we're mapping with toString. And so if you look at this pipeline, it kind of looks like something. And so does anyone does this remind anyone of anything? It reminds me a lot of a promise chain. So instead of calling map, we call .then. Instead of calling flat map, we call .then where we return a promise. And so the reason that these look so similar is because they are very similar. And so the reason we need to kind of do these callbacks is because when something is async, we don't know when it's going to come back. But if we split all of our kind of transformations into these kind of very individual functions, then we can say, right, that's basically what .then is doing, is we're saying, wait until the value comes back and then apply this function. And so that's basically what effect is doing as well, right? It's saying wait until, or it's not necessarily async, but if it is async, but it's basically saying calculate the first effect, and then when you get the value of that first effect, then map it with this function. And so just like how these are very similar, generators are very similar to async or await, right? So in async await, we basically, we're doing the same thing as this, but it's a bit more hidden, right? Like all these kind of breakpoints are still there, right? So this is a breakpoint where we're operating on the number, and then we're doubling the number. And this is a breakpoint where when we get kind of this result, we're getting a promise that's kind of does this first. If it checks the 0, it's going to reject, right? And so the same kind of separation is happening in an async function. It's just kind of hidden a bit more. And it's hidden because it's only between the await points, right? Like between the await points is where everything is synchronous, right? Like to the function, everything is synchronous. But when we await, we're basically halting execution of the function. And so that's how async functions are able to work, because the function, instead of, right, in here, there's no like stopping the function. We just split all of our behavior into different functions. Where here, we have all of our behavior as one function, but we basically kind of stop it and restart it. And so just like async await kind of allows us to do that with promises, generators allow us to do that with effects. So first, we have a synchronous effect that has a date. And so instead of await, we do this yield star. And so if you kind of squint your eyes, it almost looks like await, right? So it's also 5 characters, I guess 6 with the star. And so if we yield this effect, you'll notice that we don't get an effect back, we just get a number. And then instead of mapping, we can just kind of do the thing. And then if we want to flat map, we just yield another effect using the value that we've already gotten. And so something like really cool is that this divide function, which remember returns either a number or an error. Well, this z that we get back after yielding it is a number, right? So where did the error go? The error has automatically propagated to the result of the generator function. And so this is really, really powerful, right? This is kind of where I talked about you don't have to manually inspect the error and return it at every point. And so we can do this kind of, it's called like happy path programming, right? Where inside this function, the errors basically don't exist, but they're all still tracked on a type level, right? They're all still getting passed through. So generators are really, really common. You'll see them all over. If you go to the documentation, there's like a generator version and a pipe version of everything, and the generator version is actually the one that loads by default. You have to click to the pipe version. And this is because I think everyone is very familiar with async await, right? This is something we use basically all the time. And so generators allow us to write code that looks like async await code, right? Where this code is very functional, right? Like we have everything is a function, we're piping into functions, more functions. Where this, right? Again, if you squint your eyes, you're like, wow, this almost looks like async await. But everything you can do with functions, you can do with generators. Everything you can do with generators, you can do with just functions. It really comes down to your style. I find that there's some things that I could do in a generator that I like doing in pipes. I find there's some things I could do in pipes I like doing in generators, and so it's really just up to you. The next thing I want to talk about is this underscore function. Why is it necessary? The reason is for the types, right? To get this kind of really crazy type stuff going on where we're able to propagate these errors, if you don't use this underscore function, it won't work on a type level. Like theoretically, we could, it's possible to kind of get this to work just by calling yield without the underscore function. But to get the types right, that's required. And so it's called the adapter. And so you can kind of alias it to whatever you want. So the $sign character used to be kind of popular. Now I think the docs use underscore. I like underscore. But you can do whatever you want. The other thing with generators is often they can be a bit kind of verbose to write out this like function star and write out this yield star. And so if you go to the bottom of the README, there's some snippets for VS Code that I use a lot. And so there's basically 2 that I use, which are these 2. And so what these do is if we go to here, I can type EG and press tab, and that's going to make the generator for me. And then I can type const1 equals, and I type YY, and that types that out for me. So that makes things pretty fast. Again, that's at the bottom of the README if you use VS Code. And if you don't, it's probably pretty easy to translate to whatever you do use. The one other thing that is kind of nice about the adapter, because even though we're forced to use it, we actually make it a pipe. So instead of having to use pipe, inside the adapter function, you can just give it a value and a list of functions. And so what this is going to do is it's going to take this effect, pipe it into this map, and then yield the result of all of that. And so the final thing we're going to look at is the pipe method. So the pipe method is available on basically every type and effect. And all it does is instead of calling pipe with the value as the first argument, we can call the pipe method, and basically the value has kind of already been provided. So we just do these functions instead. So these are essentially equivalent. And so oftentimes it could just be easier to type .pipe instead. There's these three functions which I want to talk about briefly. So the first is zip. So zip is basically like effect.all, but only with two effects. So it's going to take two effects, and it's going to return a tuple of the results. So pretty simple, effect.all, but two effects. So it's zipping together two effects. And so then we have this one kind of modification of zip called zip left. And zip left, you can basically think of as effect.all, and then we are going to pipe it into effect.map, and we can call this left and right, and we're going to map to just the left, So that's basically what zip left is doing. So it's combining the two effects and then just taking the result of the left effect. But of course, the errors will be combined because if both error, right, we need that kind of result or that effect that encompasses the computation of both of them to represent all of the possible errors. But it's just going to succeed with the type of the left result. And so right is the same. And so sometimes it can be a bit confusing when to use zip right versus flat map or zip left versus tap. And so what that looks like is, right, we can effect.flatmap kind of some effects. We can take like the after here and then call, right, like effect.succeed after. And so we can do that, but we can also, or how about, we're just going to effect.succeed with 12. But we can also effect.zip right. And the one thing I'm going to change here is this, right? So these both basically do the same thing. So what's the difference, right? So flatmap has this function. And so we don't have to take the argument from this function, but it gives us the argument. And so what that is the value of the previous effect, right? And so the difference here is that zip right doesn't kind of depend on the value of the previous effect, right? So zip right is just saying, I have this effect, do this effect first, and then return the result of this effect. Where this is saying, do this effect, and then construct the next effect based off the result of the previous effect. And so it's a bit of a semantic difference, but really it doesn't matter. Like you can just do this, but if semantically you want to like be as meaningful as possible, right? I would say that there is some kind of difference where this says again, I depend on the result of the previous effect, where zip right says I do not depend on the result of the previous effect. And so that goes the same with zip left and tap, right? Because zip left is going to take the result of the previous effect, or the first effect, and discard the result of the second effect. And it's very similar to tap. Or I guess there's a function I think called tap. Yeah, okay. And so if you want to ignore basically all of that, there's a function called and then. And then is basically a combination of everything we've looked at. So and then can take a value, and then can take a promise, and then can take an effect, and then can take a function that returns a value. It can take a function that returns a promise. It can take a function that returns an effect. And so if you ever want to do something after an effect, you can use and then. The one thing to notice about this, though, is we talked about the difference between sync and try and promise versus try promise. If you call and then with a synchronous function, it is going to be equivalent to sync, where it's like, where it says basically, I am trusting you that this function will not throw. But if you call it with a function that returns a promise, it's going to actually not trust you. So slightly different behavior there. I don't know why. I would say I'm not personally a big fan of doing this. I would kind of wrap these into their own synchronous effect, like effect.sync with this computation or effect.promise with this computation. And then you're a little bit more explicit about, like, am I saying that I trust this function not to throw, or am I saying I trust this promise not to reject? But combining two effects and then can make things pretty easy if you're like, there's 5 functions, I don't know what to use, and then. So to recap on that, we have these 4 combinators, right? So just to recap, map, we take an effect, we have a function that returns a new value. And the effect that returns will be the first effect, and then taking the success value of the first effect and calling the second effect with it. Also, it's in the README, but I forgot to mention the slides, they're a web app. There's a link in the README to the slides. They're all available for you after. They're also, if you want cd into the slides directory and you run dev, you can run them locally if you want to. They're all available in Markdown. There's a slides.markdown file, so the slides are all there for you. Flat map transforms the value of one effect into another effect, right? So we take the first effect, take the value, and we have a new effect that uses that value, and flat map kind of combines them. Tap, we perform a side effect on the value of an effect, or the kind of success of an effect, without affecting the value. And all, we're merging multiple effects into a single effect. So far, we've kind of danced around error handling. So we've looked at errors, but we haven't really kind of seen how to handle errors. And so now we're going to look at how to handle errors. And so Effect has really, really powerful error handling. And this is all kind of based around the fact that, again, errors are tracked on a type level. So in this example effect we're going to use throughout this next snippet, we have 2 kinds of errors. We have this foo error, which again has this tag kind of denoting it as a foo error. And we have a bar error. And something you're going to notice is classes, right? For a functional framework, classes are actually used quite a lot in Effect. And the reason for this is that you're able to do a lot in kind of very few kind of characters or lines of code, right? Like this is constructing a type, right? Like we would have to make a type called bar error that has, right, a read-only tag, and then we have to create a constructor function, right? I think so. We'd have to create a function called bar error, and that's going to take like the arguments and return a bar error. And so class is doing all of that at the same time. It's the only way to declare a type and a value at the exact same time in TypeScript. And that's actually another thing that's very common in Effect, declaring types and values that have the same name, right? So in Effect, we have effect that's going to have all the functions of an effect, but it's also at the same time it's a namespace that has types, right? So the effect.effect type, or if we kind of never, right? So the effect type is a type is an interface within the effect namespace, right? Where this is a value on the effect object, right? So types and functions are all on the same kind of one effect thing that you import. So classes are very common as kind of a really, really fast way of kind of prescribing behavior. And so we'll see them later, even extending classes. So Effect will give us classes that we can extend with our own classes, and these kind of are able to create a lot of behavior and kind of very, very quickly. So this example we're going to use, and we can kind of change the behavior of it. So we have these 3 conditions. So I set them all to true right now. And so if the first condition is true, we're going to fail with a foo error. And if the second condition is true, we're going to fail with a bar error. And if the third condition is true, we're going to do this thing called die. And so die sounds a little violent. And that's because it is, right? So I talked about defects. And so die is going to create a defect. And again, this is like a panic in other kind of in Go or in Rust, or a uncaught exception in other languages. And this is something that we don't expect to happen, right? This is like our program is in an invalid state. Something is terribly wrong. We need to end the program now. And so this is called an unexpected error. And so unexpected errors are not tracked on the type system. So if we look at here, we have the foo error and the bar error in the error type parameter, but we don't have the boom. Because when we have an unexpected error, it's unexpected, right? We have no clue what it is. And so those are not tracked on the type system because it's really not worth kind of expecting them to happen if they're unexpected errors. And there are actually ways to recover from defects. We're not going to look at those right now. But if you do need to recover from a defect, there are ways to do that. So we have this effect. And so this effect can either fail with a foo error or it can fail with a bar error. And that's like encoded in the type of that effect. And so the other thing to kind of talk about right now is short circuiting. So effects, we talked about laziness, right? Effects, as soon as they hit their first error, if there's no error handling logic, the entire program is going to stop right there. And so if we have this effect, that's going to log to the console. And also, in effect, so this is like uppercase C console. And so this is actually importing console from effect. And the console module in effect is basically, it has all the same functions as the lowercase c console, except they're effects. So uppercase C console.log returns an effect. And so that way you don't have to basically do effect.sync, right? Console.log, lowercase console.log, right? So instead, you can just do uppercase console.log. The other thing about this is, and we'll talk about this a bit more later, right? We have services. It's possible to kind of swap out the behavior of this console. And so we might cover that later, but that's something cool you can do, right? So if in this function, right, we are consoling 1, we're failing, and then we have 2. And so this 2 will not run because as soon as a failure occurs, the program's going to stop, right? It's going to fail with that error. And so the first function we're going to look at to handle errors is called catch-all. So catch-all is similar to try-catch, right? We're catching, but unlike try-catch where we get unknown, here we get a typed error, right? We get foo error or bar error. And this is because our effect up here, we've said the only possible errors are foo error or bar error. So if we catch all of the possible errors, right, we get either a foo error or a bar error. And then this is, again, where the tag becomes useful, right? So in this function, we can kind of do different things based on the tag. But actually, there's another function that does this for us, and that's called catch tag. And so catch tag, if we kind of autocomplete here, is it's going to look at the error type, and it's going to see all the possible errors that have that underscore tag field. And so we can handle the error where it's a foo error, and then the function that kind of handles the error is only going to give the foo error. So this is only in the case where there's a foo error, and then we can return an effect. And the effect that we return from these catch functions, this obviously it's an effect. So it could be a success or it could be a failure. And so if we wanted to fail instead, right, we could fail with now a string instead. And so this is basically saying instead of a foo error or a bar error, now we're always failing with a string. But you can have other kinds of other kinds of logic. So maybe specific kinds of errors you're succeeding, where other kinds of errors you're kind of continuing the failure. And so back to catch tag. So catch tag, and you also, of course, I didn't explain. We're taking the errors, and so this is the effect from the top, the example effect, which can either fail with a foo or a bar error. And we're calling .pipe, and then we're piping that into catch-all. So that's how we're kind of incorporating the catch logic with our previous effect. We're piping the previous effect into the catch function. And that's going to return an effect that is the previous effect plus the catch logic. And so if we, again, notice the return type of the catch-all, the error type has gone to never because we've caught every possible error. In the catch tag example, the error type is now bar error, because before it was bar error or foo error. We've caught the bar error, and now all that's left is the foo error. There's also a function called catch tags. So catch tags is basically like catch tag, but multiple tags at the same time. And so what it does is it takes an object where the keys are the tags, and then the values are the functions to catch for that error. So in the foo error, we have the foo error. In the bar error, we have the bar error. And so again, this one, the error channel is now never, because we've caught all the possible errors. And so there are a lot of functions for handling errors. If you go to, and I think it's important to introduce the API docs. Not all of you may be familiar. So the API docs are available. I think the link is on the Effect website. If you go to docs, and then you go all the way to the bottom, you go to API reference, those are going to be available here. And so this is where I talked about it looks overwhelming because there's a lot. But if you go to Effect, and this is how you can kind of find functions, not brand. If we go to Effect, there we go. And they're kind of split into categories. And so I believe there is a error management category. Yeah, right. So error handling. And here are all the error handling functions. So there's a lot. We're going to go over just a couple. And so the next one is called or else. So or else is kind of similar to the kind of flat map versus zip right thing we talked about, where catch, like all the catch functions are kind of doing something based on the result of the error. Where or else, you'll notice this function doesn't take any arguments. So or else is saying, I don't care about the error. Just whatever it is, do this instead. So or else kind of implicitly handles all the possible error cases. And so here we're saying, no matter what the error is, if an error occurs, instead succeed with this effect. And so you might be wondering, right, like if this function doesn't take any arguments, why do we have it behind a function to begin with, right? Like we could kind of, in theory, just do this, kind of like how zip right works, where we don't put it behind a function. And the reason for this is because there is some kind of cost to constructing this effect, right? Like it's an object, we have to allocate that object. And so we kind of assume that things are not going to fail, right? And so we kind of say that, hey, like we don't need to create this effect, create this object, until the effect fails, right? When the effect fails, then we can run this function and get the failure. And so that's kind of why this is behind a function, even though it doesn't take the error as an input. The next function, or else fail. So or else fail is basically like or else, and I think there's an or else succeed as well. Yeah, so or else takes an effect, where or else succeed and or else fail take values, but they're automatically mapped to either the success or the failure channel. So or else succeed takes just a value, not an effect, and always succeeds with that value. Or else fail takes a value and always fails with that value. The next thing is map error. So map error is going to modify the type, or it doesn't have to modify the type, it can just modify the current error. So before, right, we had foo error or bar error, and now we have a function that takes the foo error or the bar error and just returns an error. And so now this is error, right? And so this is very similar to map, except instead of mapping on the success channel, we're mapping on the error channel. Another function we have effect.match. And so effect.match handles both cases at the same time. So here we're saying if the previous effect succeeds, then this kind of resulting effect should succeed with this string. And if the previous effect failed, then we should succeed with this string. And there's also, these kind of always map to the success channel. But if you want to map to effects, there's also match effect. And so match effect is the same thing. We have on success, this is going to return an effect. And on failure, this is going to return an effect. And of course, these are effects, so they could also fail. Next function, first success of. So you're going to give it a list of effects, and it's going to give you the first effect that succeeds in those lists, so it's going to run them in order. There's also retrying, there's timeouts, there's kind of, I talked about that short-circuiting behavior. If you want to opt out of the short-circuiting behavior, so you want to kind of accumulate errors, there's a way to do that. There's ways to do that as well. And so lots of possible error handling strategies. We'll kind of look into some of them in the example apps, but there's basically every kind of operation you might want to do on errors, ways to kind of handle errors you are able to do. And so now I want to talk about how to handle errors in generators, right? All the functions we've kind of looked at so far have been pipes, right? Like we take our effect, we pipe it into these error functions, these catch functions. And so how do we handle errors in generators? So there's kind of three options. And so the first is to just wait until the end of the generator to handle the error. And so this is where I talked about like the happy path, right? So here, we're not doing any error handling at all in the generator. We're just saying, if there's an error, kind of pass the error on, but within the generator, this is only the happy path. This is only the success path. And then, right, this whole effect.gen function returns an effect. So we can then call pipe on that, and that's where we can put our error handling logic. So we have the effect with the happy path, and then we pipe this into our error handling logic at the end. The other option is doing the error handling inside the adapter pipe, right? So here we're yielding an effect that might fail. So this is an effect that might error. And so inside the adapter pipe, that's where we're doing our error handling. And so this is going to be a number, and this is going to have never, because what this does is these kind of combine, and so then we yield that error, which we've already handled the error, or that effect, which we've already handled the error. And then finally, both of these options, what they don't do is give you the error as a value inside your generator. If you want the error as a value inside your generator, there's basically one way to do that, and that's with effect.either. And so I know we kind of talked about the either type a bit before, but the either type, we'll talk about even more in a second, but is basically a union. It's a kind of union of two things. So there's a left type and a right type, and the either is two things. And so what effect.either does is it takes an effect, right? So we have effect kind of like string number, and it's going to convert that effect into a effect either string number. And so what this is doing is it's moving the error channel into the success channel. And so that way, when we yield, so this effect might fail with a number or an error. When we call effect.either, now this is going to return a, it's up here. It's going to return an effect of either a number or an error. And so that way, when we get this, now we can discriminate within our generator. And so if it's, then there's a bunch, well, again, we'll talk more about eithers later. There's a bunch of ways to figure out kind of which side of the either you have, left or right, how to operate on that value. But kind of in theory, we have an is right. And so if it's right, then we know that this represents the success, right? This is the number. And if it's left, well, we know that this is the error. And so that's how we get the error as a value within the generators. We use effect.either, and then we can discriminate whether it's a success or an error. All right. Back to the slides. So we have a recap slide for this, right? So catch all, we recover from all errors. Catch tag from one error, a tagged error. We have map error, it's like map, but on the error channel. We have match to handle both cases, and we have either to move the error channel into the success channel. So any questions about error handling? Okay. Yes? Yes? Yeah, we can take a look. So the question was, I talked about effect.die, and so how to recover from defects. So yes. So the question was, what are some scenarios where we want to recover from defects? And so I think some scenarios, I'll get to both. Some scenarios where you want to recover from defects are probably when you're interacting with non-effect code, right? So, or I mean, it's kind of arguable there too, right? Like if you have a defect, the run functions are just going to throw. So then the non-effect code is probably expecting, if there's an error, just to throw as well. I would say, like if you have, I was going to say if you have some resources to clean up, but we'll talk about resources in a sec. And in resources, in effect, they automatically close even if there's a defect. I don't know. There are definitely scenarios where you do. I would say most of the times, in effect, you basically always want to type your errors, right? Ideally, like you're typing every error. And so ideally, you're only throwing, or you're only dying in scenarios where you don't want to recover from it. And so again, if you don't have to do that, but any scenario where you would want to recover from an error, I would say you should just not die. You should use a typed error. But let's look at two things. So one, we're going to look at how to recover from a defect. So I'm going to call this const defects, and this is going to equal effect.die. And then what I'm going to do is I'm going to pipe this into effect.as. And so effect.as is a function that, and this is actually a value. Something you'll notice, is this not a value? I think this takes a message. There you go. And there's a die message. There's a couple other, there's a die sync that takes a function that then generates the message. But just die, I think, takes a string. And so as kind of purely, what as does is you can kind of think of as like a zip write, where it's basically saying whatever the previous effect did, this is now going to succeed with 0. And so this is sometimes useful on like a type level, where if we have a function that always fails, right? So for example, we have effect.fail and just some kind of string. Right now, this has effect.number present, even though this effect will always fail immediately. On a type level, this is saying like, hey, if this first effect didn't fail, this is going to succeed with a number. And so it can kind of be useful for having effects that are not, like if you know an effect is going to fail, or basically it's remapping an effect to a specific value no matter what. So we're saying whatever this effect is, kind of remap it as 0. And so in this case, it's just kind of remapping this failure to have a success type. I don't think I'm explaining that the best, but back to die. So this is going to create a defect. So if and I'm actually going to move this to the pad. So this is just like a scratch pad. So I'm going to import effect from effect and here, and then we can effect.run sync defects. So here we get our defect, right? It's logging out the error, exiting with a non-zero exit code. So if we want to handle this error, I'm going to rewrite this a bit differently. I'm going to rewrite this with pipe. I'm going to say defects, and then I'm going to pipe this into effect.run promise, or run sync, actually. And the reason I'm doing that is so that we can put some other function in between here, right? And so here we're going to effect.catch. So there's catch all defect. There's catch some defect. So I'm going to say catch all defect. And this is going to give us the defect. And it's going to take, I'm just going to say effect.succeed 0 for now. Need a comma. And the defect is of type unknown, right? Because we have no clue what it is. It's like try catch. And so this is how you would do that. There's catch some defect instead. And so some defect is going to give you a way to say, to kind of inspect that value, where this is going to, no matter what the defect is, we're recovering from it. Where catch some defect is going to give you a chance to say, here's the defect I want to recover from. Here's a defect I don't want you to recover from. And if you don't recover from it, obviously it's going to continue to defect. And so if we do this instead, obviously it's going to succeed. The one other thing, and again, we'll talk about exit in a second, but if you run sync exit, we're going to get an exit. And we can just talk about this now. So an exit is conceptually equal to an either of the A or a cause E. And so I can't type. So an exit is basically either the success or this cause type. And so the cause type represents a bunch of possible failure cases, right? Because having one possible failure case might seem powerful, but what about when you have parallel errors, right? Like when you're doing two things concurrently and they both error. Are we going to return the one that happened first, or are we going to return both? And so in cause, we can, so there's a function if we import exit, there's exit.match, and so we can pass it our exit, and then we can give it, right? So exit is an either, right? So there's either a success or this cause. And then inside the cause, we can import cause, and we can match on the cause. And the reason I'm matching on this is so that you can see all the match arms. And so you can see that, so here are all the possible kind of members of the cause union. So there's empty, which basically represents no error or success. There's just a simple failure. There's a die, which represents a defect. There's an interrupt, right? If like something gets interrupted, that's, so you can think of the cause as kind of like the output of a program, right? So a program, it's kind of simplistic, again, to look at it as either a success or an error. So here we can say it either succeeded or it failed or it died or it was interrupted. And then we have these either sequential errors or parallel errors. And so the cause data type is kind of how, even without kind of catching a defect, we can encode the result of our program handling kind of these possible cases that are kind of more advanced than just success or error. Does that answer your question? Okay. So the next thing we're going to look at is context management. So I talked about effects third type parameter, right? And so in effects third type parameter is where it stores the types of the services. Oh, I think we're at 11 here. So we're going to continue this first part. We're most of the way through it when we get back, but we are going to take a 15-minute break, definitely get some water, and yeah, thank you, everyone. So we'll come back at 11:15, I believe. I think we're just going to go ahead and start. By the way, we are a bit behind schedule, but like I said, we're probably not going to get to everything. That's totally okay. What's probably going to come out is like the second half of the second app, but we are definitely going to get to the final part at the end for sure. So that's really important. So there were a couple questions during the break that I want to kind of answer to everyone. And so the first was about how to handle kind of excessive nesting of pipes. So we have a pipe, and then inside our pipeline, we're piping even more. And then inside that pipeline, we're piping even more. And so there's a couple solutions to that. One, this is not really a solution, but it's something kind of good to know about, is this function called flow. And flow is basically a pipe, but without the kind of value as the first argument. So instead of kind of composing functions and then applying it to the first argument, we're just composing the functions, and that's going to return a function that represents kind of all those transformations. And so this can be useful for kind of separating out logic. So if we want to kind of declare a bunch of functions kind of externally as one function, we can use flow to do that, right? So here we have these functions, and flow is going to be a function that takes some input, the input to the first function, and then calls the first function, calls the second function, calls the next function. The one thing that is kind of hard about doing this with effect is that you lose a lot of type inference, right? So if we try to like map and catch all and map, we don't really get the type inference that really powers a lot of the effects functions. And so this is something kind of good to know, but something I don't think I've ever used flow, really. The other solution, and there's a whole dedicated docs page to this. It's on the left. If you scroll down to code style, to simplifying excessive nesting, the kind of most simple solution is just to use effect.gen, right? Because in effect.gen, we can, to kind of show the thing we're trying to prevent here, we have this. And the reason this happens is because we have effects that are dependent on another effect that are dependent on another effect. And so we have this kind of series of indentations. And so with effect.gen, we can kind of store the results of previous effects in one function, right? Rather than having, this is like the same as like the kind of callback hell with promises, right? Instead of needing excessive callbacks, we can store the results of previous computations. So the question I had was, they want this kind of ability to store values without creating more callbacks, but they don't want to use generators. They just really like pipes, right? And so the solution to that is this function called effect.do. And so we have this do simulation, which is a very functional thing if you come from like Haskell. But this is actually doing basically the same thing. So here we're declaring variables, right? We have a variable that's the result of an effect. We have a variable that's the result of an effect. Here we're binding the result of an effect to this like string value. And we're binding the result of this effect to the string value. And what this is doing is effect.do actually returns an effect whose like success is just this empty object. And instead of having like a function scope, this object represents the scope. And so when we declare a variable, we're just giving this object a value. We're giving this object a value. And so you can see we can kind of use variables from our scope by kind of unwrapping the result of the previous effect. So we can create a new variable based off the previous variables, and we can kind of look at the current variables because they're just an object. And so that's a way, if you don't want to use gen, to kind of simplify the excessive nesting. So now we're going to talk about context management. And context management is, again, the third type parameter I talked about, where we can store these services or these dependencies that an effect requires. And a question I also got during the break was, when do you kind of, the difference between function arguments and these effect dependencies? And so you can kind of think of this, right? Like if we have a function called like add1, and this takes a number and it adds 1 to the number, right? Like the number that we're passing to it is kind of like the most simple dependency to this function, right? Like we're giving this something that it requires before it can run. And so in effect, you can create functions like this the same way, right? You can have add1, and this can take a number and return a effect.success. That is success. Succeed x plus 1, right? Like you can do this. And that is totally okay. That is a very simple way of providing some kind of dependency to a function. But the other thing that you can do, and we'll see in a sec, is you can also create, like we can declare a add one service, and this is going to be a effect.effect that returns a number, never requires like a x service. And we could just say type, or don't worry about that for now, right? And so this kind of conceptually is very similar, right? So here we're requiring some dependency through a function argument. Here, this is not a function, right? Like this is just a value. And we're requiring the dependency through this kind of dependencies type parameter. And so it can kind of be a bit of a blurry line of when should we pass something to a function and when should it become a dependency, or like a service, that's what they're called. And so my answer is there's kind of different categories of things. So if you have like a database, right, like that's the best example. A database is something that is not really kind of specific to this function, right? Like we have lots of functions that may require a database. And so a database is something also that we might use kind of a lot through our application. It's something that we might want to swap out the implementation of. And so that's a really good candidate for something as a service. But if you have a function called like getById, you could make the ID a service, but it doesn't make a ton of sense, right? It probably makes more sense just to create a function that takes an ID and returns an effect with that ID. So with that said, what are services? So services are some kind of functionality that an effect requires to run. And they're defined by their type signature. And the reason that they're defined by their type signature is because when we use the service, we use it completely independently of the implementation of the service. So we use the service just by its type signature. So we get the service and we get something of the value of the type of the service. And then we can use that thing because we know the types. And then later, somewhere else, completely separately, we can provide some value as long as it's the same type. And so that's kind of where we can depend on services based on their types and provide services, again, based on their types, but these are very separate things. And so now we'll look at kind of how that looks in practice. So here, we're defining the type of our service. So this service is going to be a service that generates random numbers. So it has one property called next and one function called nextIntBetween. And so a lot of the times with kind of random things, you expect next to be like a method, right? Like we call next, and that's because without effects, the only way for something to be lazy, and of course generating a random number is something that we want to be lazy. We don't want that to happen until we call next. Normally that's a function. But a lot of the time in effect, if you have a function that takes no arguments and returns an effect, most of the time that can just be a value, right? Like this is just a value. There's no need to make this a method because usually constructing effects is pure. It doesn't have side effects. That sometimes isn't the case, but most of the time there's no need to make a function that has no arguments that returns an effect. You could just make it a value. So we have a value that is an effect that returns a number, and we have a function that takes two numbers and returns an effect that returns a number. So this is the type of our service. And so now we're going to create a tag. And a tag is a placeholder for our service. And so the tag is a class, and this is where I talked about using classes. And so there's a way to do this without classes, but classes make this super convenient, right? This is literally a single line. And so we extend context.tag, and so we import context from effect. And so we give it a couple things. So we give it a string tag, and this is important because this does two things. So this is what separates it in the types, right? So if you have two tags that have the same like interface and the same string tag, actually I don't think it's the interface. But anyways, what's really important is that these tags are unique throughout your application. That's very, very important. Because on a type level and on a runtime level, the string is how effect is going to map your tags to your services. So basically how it's going to inject the services at runtime. So it's very, very important that these tags are unique between your services. So a lot of times what you'll see is you can have like a at app, like the name of your app slash like the module slash like random, right? And so if you do that, very unlikely you'd name something else the same thing. But it's very, very important that these are unique strings throughout your entire application. And so then this takes two generics, two type parameters. So the first is actually the class that you're defining. So this is the same name. We're using it within its own definition. And the next is the type of the service. So this is the type of the thing that we are consuming and the type of the thing that we're injecting later. And so this is where, and you can define this like inline, right? Like we could define this down here, but you can also define it externally. And so the class random, again, this is a tag. And so the tag we are going to use in our effects as if it was the real thing. And then later, we're going to provide the thing. So let's take a look at using it. So using it is as simple as calling yield on the tag. And so this is the same as like you could also effect.map random, and then you'll see here in a second. So random, these tags, they're what's known as a subtype of effect. So we can use them anywhere we would use an effect. So just like we would yield an effect, we can yield a tag. Just like we would map an effect, we can map a tag. And so there's a couple types like this that we'll look at. And so these are very useful because all of the effect functions we already know are going to work with all these types that are subtypes of effect. So when we use a tag as an effect, what it's going to give back is the type of the kind of implementation we told it, right? So now we yield the random, and what this is doing is it's getting the, it's at runtime, right? There's going to exist some real value for this service, and so that is what's going to be returned here, right? But this is completely independent of whatever that ends up being. So then, just like as if it were the real thing, we can call next in between. And we could call next instead, right? So this random is whatever type we said it would be. And you'll notice that when we consume this random tag, the random is now going to appear in the third type parameter, right? So this is saying this effect requires something of the random type, like the random service, to be provided to it before you can run it. Because if we don't do that, like there's no way to run this without a random. Like the code doesn't work, right? And so you'll see that we get a type error here. And if you scroll to the bottom, it's going to say type random is not assignable to type never, right? The third type parameter must be never before we can run effects. And so what we need to do now is provide the implementation of the service. And so the way we can do that is create like some object that represents the actual implementation of that service. And so the really common way to name these is live. So this is random live. And the reason it's called live is because this is what's going to be used when the program is actually running, right? Like at runtime, this is the live version of that service. So here, right, we just return effect.sync math.random. Here we have a function that returns effect.sync math.random with some more math. And so now what we can do is use the effect.provide service function. So we're taking our program, which again requires a random, and we're piping it into effect.provide service. And provide service takes two things. It takes the tag that you're providing, and it takes the thing of the type of that service. And then what we get out of that is the effect without that service requirement, right? We've fulfilled that requirement, so now so now that effect no longer requires that service. And then we can run that effect. So if we run that, we get, this is 8. I need a dash. That's because there's a declare somewhere here. I forgot about that. But in theory, if we run this right now, what's going to happen is it's going to execute this effect. And when it gets to here, it's going to say pull whatever the live implementation of random is that you've given me from the context. There's this thing called the context that stores all of the services. So it's going to say, give me the random service from the context. And it knows what service is which, again, by this string identifier. That's why it needs to be unique. And then it's going to give it whatever you provided it, and then use it. And so, again, you can start to see how this can be very useful for, we can create tags for a database, or we can create tags for a logger, or we can create tags for all kinds of things. And just like how errors kind of stack up, we can have effects that depend on multiple services. And if we only provide one service, all those other services are still going to be there. And only when we've provided all the services, that's when it's finally going to be runnable. Does anyone have any questions right now? Yes?
Is this kind of tagging also possible with errors?
Okay, great question. So they said, is this tagging kind of also possible with errors? So I would say this tag is very different from like the underscore tag field, right? Like, right? This tag is not the same as this tag. And so like with errors, like you wouldn't really want to create a service for an error. You want to create services for like functionality. And so does that kind of answer your question? Yeah. Okay. Yeah, so the service can be anything. The service could be a value, right? It could be a single constant. It could be a big object, right? And that object could have functions that do anything, right? It could be normal functions. It could be functions that return effects. The service could be an effect itself, although that doesn't make a lot of sense. So what's a good example? Like later, this kind of later in the app we're going to rewrite, at one point we create like a WebSocket server, right? And the WebSocket server is a class, right? New WebSocket server. And so what we do is we create a tag that represents the WebSocket server. And so we can use the WebSocket server in our effects and then later provide the WebSocket server. So that's one example.
One point where the context tag was supposed to be a symbol to then show real.
Yes. So yes, the tag API changed quite recently. And so before, you used to have to do a couple things. Like there would be 2 different types you'd have to declare. There would be one type, and there still kind of is that, right? Like there's the implementation type and the kind of identifier type. Like these are kind of 2 separate things, and this is important for how effect implements this, right? All you need to know is that like this type is the type of the thing, right? The type of the thing you're using in your effects, the type of the thing you're providing is this second type parameter, that. And then this is how effect, because effect, like just from this type, there's no way for effect to like kind of figure out, like when you call, when you use this service, effect has to know which service it is. It can't do that from the type of the thing. And so that's where this string tag comes in. Again, it used to be, like you used to have to declare like a unique symbol type, but now it is only based off the string. I mean, let's see. Let's see. Michael might know this, but
Yeah, here. Usually, when you do things in library, then you want to prefix the string identifier with kind of the package name, or make it unique. In application code, usually the name of the type is unique enough because you're not going to name two things the same way. But yes, you can think of the context of an effect as a map where you have keys and values, and the identifier you put there is the key that binds to a specific implementation. So if you have two things with the same key, they collide.
yeah, so that's where I talked about. So if you have, like, in your app, this is a way that, like, again, you can almost surely make sure that you're not going to interfere with anything. If you're using a library, you can call this the name of your library. And then also on the type level, the example I want to show here is, let's see, here. If we get rid of this, so this is an example of like an external library tag. So this server type comes from some other library. In this example, this is like a very far example, but this is an example of a tag that does not come from a library. Like this is not a tag I declare. This is some library tag. And so in your effects, it is like you can't see the kind of prefix name. I think there might be a way, but basically if you are declaring tags that have a very generic name in a library, it might be useful to name them kind of more specific to your library names. And so that way, again, here server, I don't really know where the server is coming from. Like I do, because like I know what library it's coming from. But if you have a library that, what's like something super common? There's also like a couple of names I think effect uses internally. Like if you're making something called logger, I think it's kind of a fine line. Like obviously, if you know how you're using your own services and you want to give them very common names, but in a library context, it might be useful to give them more descriptive names kind of unique to your library. Hopefully, did that answer your question? Yeah. Okay. So next we're going to look at, with this function, effect.provideService, you'll notice that the service we're giving it is just a value. Like it is one value. And so you might wonder, well, how do we create services from effects, right? Like let's say I have an effect that generates this random thing. Probably creating this random thing. A good example of this, actually, for random, is let's say we want to generate a seed, right? Our random thing has a seed, and we want to generate the seed. And the generation of that seed is a side effect, right? Like we want to effect.sync generate the seed, right? And then we want to construct our random service using that seed, right? So basically we are constructing the effect effectfully. The way you can do that is this layer type. And the other thing the layer type does that's really important is when our dependencies themselves have dependencies. Those are two separate use cases: creating dependencies from effects and creating dependencies from other dependencies. So for the first one, right, like let's say we are going to const make random. And this is going to be a effect.sync. And this is going to, let's just say, generate. I'm going to call math.random here, but let's imagine this is like generating the seed, right? Like it's doing something effectful. And then we can pipe this to effect.map. And then we're just going to throw this exact same thing in there. And so now, instead of a random impl, right, we have a effect that succeeds with a random impl. And so the way we can the way we can create, the way we can create services from effects is using the layer thing as I talked about. So layers have 3 type parameters, very similar to effects. And so like effect has a success, an error, and a requirements, a layer has a out, an error, and an in. So the out is what services this layer creates. So, as an example here, we can call this random layer, and this is going to be layer.effect. It's going to be random, our tag, and then the make random. That's not right. Layer. And this is something you also need to import from effect. So now this is a layer that returns a random, or generates a random. And so layers can represent the effectful creation of services. And so instead of using provide service up here, what we're instead going to do is a slightly different function. We're going to call this runnable2. We're going to effect.provide, and we're going to provide the random layer. And this is going to do, after TypeScript, I'm just going to, oh, of course. So the reason why you don't need to provide the tag is because the layer itself describes what services it produces, because when you create the layer, you give it the tag there, right? So when you provide a layer, and the reason for this is because layers can provide multiple effects. And so we wouldn't want to pass multiple tags, but we can create a layer, and you can create a layer for one service, create a layer for another service, and there's functions to merge layers, so we can then, from a layer for each service, we can create a layer that can create multiple services. And so kind of just like how in effect, you can kind of combine your effects and then you run one effect, you can create layers for all your different services and combine all your layers and then provide one like main layer to your effect, right? And so what this is going to do is, I like to think of it as kind of the opposite of flat map. Not like exactly, but conceptually, where flat map is going to do an effect after the first effect. Creating a layer from an effect is going to say, execute that effect first, and then run the main effect with the result of that effect as the service, right? So layer is this kind of world that happens before your program, right? And so you can do lots of things in layers, right? We can establish a database connection. We can start a logging kind of connection. We can do all kinds of things, and that happens before your effects, and then your effect starts. And so layers, because they can come from effects, they can error, right? So that's where this error, the second type parameter, comes in. So if you create an effect, a service from an effect that can fail, that layer can also fail. And then finally, just like how effects can have requirements of other services, layers can require other services. So here we have an example. So I have two tags. So we have a tag that is a feature flags. And so feature flags has one function which takes a string and returns a effect of a Boolean. And then we have another tag called a config file. And the config file basically represents the contents of a file, kind of a JSON file that's parsed to an object. And so when we implement the feature flags, we want it to basically depend on the config file. So we're creating a layer from an effect for the feature flags tag. And first, we're using the config file tag, right? So this is equivalent to yielding the config file. So we're saying, give me the config file from the context. And then with that config file, I can use it in this next function, right? I can say, I can make an isEnabled function that's going to read the contents of that file. And like if it's true, we can return true, otherwise false. And so then this layer now depends on config file. And so if we want to use this layer, we first have to give it the config file. And so we can kind of generate this tree of dependencies where everything's tracked, right? And so then our config file is also going to be an effect, because first it needs to read the file, right? That's an effect. And so we're reading the file in try promise, and we're using fs from node. And so we're reading the file, and then we're parsing the file with JSON.parse, again, with try for errors. And then that's going to generate the config file layer. And so then we have this main function, and this represents a function that uses feature flags. And so if we just try to provide feature flags, right, it's going to say, hey, you can't run this. Like this still depends on config file, right? Because feature flags depends on config file. We haven't provided config file. We've only provided feature flags, which also depends on config file. So what we can do is provide from layer, right? So we can have one layer and provide it another layer. And so if we provide the feature flags layer, the config file layer, then we get this final layer that has no requirements. And that layer generates the feature flags. We can provide that to our effect and run it. So layers are a way to, again, do effectful things before your effects and create these trees of dependencies. We can have dependencies that depend on other dependencies that depend on other dependencies. The other thing that's really common to do, because we create our tags as classes, is we can define the implementation in one place. And you don't have to do this, but it's very convenient to kind of create a static member called live. And this is going to be the layer. And that way, when we want to provide, like we use the tag called foo, and then provide, we just provide foo.live. And so that way, you can kind of put the tag and an implementation of the tag in the same place. Again, you don't have to, right? The implementation can come from anywhere. But this is kind of a convenient way to define those in one place. Another thing that is also kind of very common is deriving the type of a service from the kind of function or effect you use to create it. And so here we have a tag, or we have a function called makeService, and this is an effect that has like an object of this shape, right? And then we have a tag where the kind of implementation type of that tag is this effect.effect.success type of makeService. And so effect.effect.success is basically just a type that pulls out the success type of an effect. So you pass it an effect type, it gives you the success of that effect. And so just like success, there's also, I think there's like fail and error, right? So we can kind of pull out the error types. And these are actually very simple, right? In here, it's just, you can't see, but it's just kind of inferring the type. So if you have an effect number, effect.effect.success number, it's going to give you number. So here we are inferring the success type of this make service, and that's going to be the type of this effect or this tag. Does anyone have any questions about this? I know that's a lot.
Well, yeah, I got in the documentation we have the power to follow.
Yes, of course. So yeah, so there's this kind of interesting dilemma where let's say we have a service called 1, a service called 2, and a service called 3. And 1 and 2 both depend on 3. If we and creating 3 is effectful, right? Like when we create 3, let's just say creating 3 logs to the console. And 1 and 2 both depend on 3. When we provide 3 to both 1 and 2, should it create 3 twice and cause all those side effects twice? Or should it create 3 once and share the kind of service that we created between 1 and 2? And so by default, what effect does is it memoizes layers. So what that means is it's basically caching the result. So in your entire dependency tree, if a service appears multiple times, it's only going to be created once. There are some kind of ways to opt out of that. And so if we go to the docs, because I don't want to get this wrong, if we go to the docs, you can, and also the reason if this is the same, there's a couple kind of nuanced things, and the docs are going to talk about it, but if you want to ensure that you're getting a brand new, not cached version, there's this thing called layer.fresh. And layer.fresh is going to basically return you whatever type you passed in, but it's going to, no matter what, recreate it, even if you've already created it. There's also providing locally, right? So you don't have to provide layers at the very edge of your program, right? Like you can provide every service your program needs once at the very bottom, but if you have kind of effects within your program, you can provide right there. Like you can provide services. Let me give an example. my code.
Layer detect too many services. Now, if I provide live to another layer, it's reusing this layer, right?
By default, yeah. But even if it's effectful, the only kind of like static service is like not an effect, right? Provide service is literally just a value. But if you're using layers, and layers, just like effect, like layers have a bunch of constructors. So there's layer.succeed, and so layer.succeed is like effect.succeed. It's going to just create from a value. And layer.sync is going to create from a function. And layer.effect is going to create from an effect. So there's a bunch of constructors. They're kind of similar to effect. But no matter how you construct your layer, by default, if you use that layer multiple times, it's going to reuse the same one. And again, there's ways to kind of opt out of that. And there's also ways to like manually memoize layers with layer.memoize. The docs page for this, by the way, is in context management dependency memoization. Does that answer your question? Okay. So now let's recap that. So if I go to here. So services are functionality whose type signature is separate from the implementation. So we define the type up front, we use the type, we define the implementation later as long as it conforms to the type. The tag is a placeholder. We can provide the service if we're just providing a value. We can provide with a layer if we have kind of more complex dependencies that depend on other dependencies, or we have dependencies that need to be created effectfully. And so now we're going to do some exercises. And I have exercises for error handling, so we're going to do that in a sec because I forgot to do them. But we're going to do the context exercises first, and then we're going to go back to the error handling exercises. So if you go into part 1, into exercises, into context, I have 2 exercises for you. And the way I've structured these exercises, I don't know if hard is the right word, but they kind of, basically my goal with these exercises is to kind of show you new APIs that I haven't taught you. And so the idea is that you might be able to discover them yourself, but if you can't discover them yourself, that's totally okay, because we're going to go over the solutions. But the idea is that you can try to kind of figure it out by yourself, and kind of how most of these end is I say, here's a kind of manual solution, and then here's an effect function that does the same thing for you. So the first argument is, and this is actually pretty hard, but is getting, so like I said, there's this context. So every effect has a context, and that's where all the services are stored. And so when you yield a tag, what it's doing is getting the context and then grabbing that tag from the context. And so the first exercise is getting that manually, which I can see Michael laughing. This is difficult, but I gave you a little hint. And so I would say the best way you're probably going to be able to figure this out is by kind of importing. I already imported the context module. But if you kind of press dot and you kind of look through the functions, you might have a chance. But again, we're going to go over kind of how that works. And then the next exercise, just kind of, or do we want to do one at a time, or do we want me to kind of explain both one at a time? All right. So let's take a couple minutes, and then we'll come back. Good luck. Before I kind of go over the solution, does anyone want to share how they try to approach this? I mean, there's actually kind of only one way, but did anyone able to get the test to pass? No, I'm sorry. This one actually was probably a bad one to start, but I think the solution will actually make a lot of sense. So if we go to context, so here's the solution. So first we use effect.context to get the context, and you can't see, but this is like a context type. And then we use context.get with the tag to get the item from the context. And so what's going on here, and we can actually, let's move this back over. What's going on here is, as Mike talked about, the way these kind of services are implemented internally is it's just a map from the tags to the values, right? So when you provide the services, you're kind of filling that map. You're saying, here's the tag, here's the value, here's the tag, here's the value. And so at runtime, what we're doing is we're getting the context, we're getting that map, and then just pulling out the value that is equivalent to that service. And so there's this function called effect.context, and effect.context is going to give you a context of some type. And that's and that type, and the reason that this is like safe is because getting the context of this type requires that the kind of resulting effect also has this type. And so what we get back is this context foo. And so this is saying this is a context that has a foo service in it. And so then we can get the context, just like kind of getting from a map. We can get the foo, the value of the foo tag, and that's going to give us back the value of kind of the tag's implementation. So again, I'm sorry this was kind of a difficult one, but hopefully that kind of helps you a bit understand kind of what's going on behind the scenes when you yield a tag. It's not super magic. What is a little magic is like where this context comes from. And we might get to that at the end, but you can just imagine that that's a bit magic for now. Yes?
In my case, I did the first one, I treated it like we provided.
Yes.
We inferred from the .py that provide the ping monster, but now I'm wondering whether it's even possible in TypeScript.
Yeah, so effect.context, if you leave this out, and this is actually probably pretty easy to do, it returns unknown by default, right? And so this is just a context, we don't know what's in it, just like some map, right? And so here we can kind of manually say that this is a context that contains a foo. So the next exercise, I think will be, yes.
Is this just an exercise, or does it have like a real life use case? Or this was just to show how.
Great question. So I would say there is some use case, although I think it is a bit obscure. Where that kind of comes in is the context module. You can create contexts manually. So we can, I'll show if we, context.
I'm asking because if you do like the basic context management file.
Yes.
And it's easier to read. So I just wrote foo equals yield.
Yes. So I would say in terms of getting something manually from the context, there's probably no real world use case for doing that probably ever, basically. Like you can always just yield the tag. Mike's shaking his head. So there probably is a use case. But what I would say the more common use case is understanding that context is like a data type that you can work with. So we can create a empty context by calling context.empty, right? And this is a context never. And then we can pipe that, and we can say context.add foo.live. That should work. Because this is not, if we, there, right? And now we have a context foo. And so these are things you can kind of make manually. And where that comes in is you can effect.provide, or what is it? Oh, okay, so in addition to taking layers, you can also provide a context. And so this is going to, you can actually see what's happening behind the scenes, right? This is going to exclude foo from the effect that we provided to. And this also has a couple other places where this shows up as well. But the context is like a whole module, and again, it's just a map from tags to services, and you can, again, this is a bit more obscure. Like most of the time, you can just yield the tag. Most of the time, you can just create a layer, provide service. But context is the module that kind of powers that, if that answers your question. So the next exercise is we have this class, or this tag. And so this is a service. It kind of looks very similar to what we have before. Right? It's a random service. It has a next int, a next bool, and a next int between. And the implementation of the service actually doesn't matter for what we're going to do. And what we're going to do instead is basically create 3 values. And so what these are going to be is instead of first yielding the service and then kind of like getting the random and then calling random.nextInt or random.nextBool, what I want you to try to do is create one value called nextInt, which is just an effect. And you'll see that this effect depends on random. So what you're going to hopefully do is create an effect that first gets the random and then does next int. So it's basically kind of the yielding of the tag, like getting the tag, and then next int as kind of one operation. So that way, again, the alternative is we yield random, const random equals random, and then we call random dot next int, where what I want you to try to do is create some value next int where you don't call random dot next int. You just call next int, and it gets the random first, and then does next int. Yes, good luck. All right, everyone, was that, most people were able to do it? Or raise your hand if you were able to get the test to pass. No one, okay. Who's close? Who needs like a bit more time? Or are we stuck? Yeah, I'm gonna start. I'm sorry if these are very hard, but I think the solution to this one is actually quite simple. And so all we're gonna do is random.pipe, and this is basically a map. Right? We can think of this as effect.map. And so we're first using the service in an effect context, and then we're just mapping to a member of that service. Right? So I can, I'm gonna bring this over here. And so we can use map to be a bit more clear, right? So kind of using a tag as if it was an effect is equivalent to kind of getting the effect from that, or getting the service from that context. And then this is the random service. And then instead of using the random service, we're just kind of mapping it to just that one value. And so that's going to return, or this needs to be flat map, right? Or not flat map. This is right, yeah. Because oh, were I think I might have messed up the test cases, or these, or no, this can be flat map. Yeah, this is right. Right, so this is an effect that is going to first get random from context, and then get next int from that random, and kind of call it or use it. I'm using the wrong words. And so these other ones are the exact same, right? Like this first function, and you can write these in slightly different ways, right? Like we can write this as a generator, right? So we can do effect.gen, and so first we can say const random equals just the random tag, and then we can return random.nextBool. Actually, we need to yield the result of random.nextBool. So that might be a little bit clearer. And so does this make sense to everyone? Yeah? And so, like I said, my goal with some of these exercises was to kind of find our way into kind of built-in APIs. So in effect, there's this function called effect.serviceMembers. Or we can look at service functions first. There's service constants, there's service function, but I think members is all of them. And so what this is going to do, functions. Oh, because these are renamed. But what effect.serviceMembers does is it gives you back an object of all the functions and all of the constants from that service, but in this kind of form where we don't have to yield the service first, which is useful sometimes. It's just a cool thing you can do. And so if we get rid of all of these, right, now we have these variables that kind of implicitly depend on the service, right? So this is just an effect that first gets the service. It's doing exactly what we just kind of implemented manually. And so there's service members, there's service functions, which just gives you the functions, there's service constants, which just gives you the constants. And so this is a way where maybe you have like a really big object that instead of kind of getting it from context, or I mean, it's all like just kind of top level properties. But yeah, this is something interesting you can do. Any questions about this? No, okay.
Just maybe pointing
Oh, yeah.
Generally speaking, anytime that you use the service to construct other services, so inside layers, you don't want to use this way because it will propagate the dependency. Like you want to separate the access from the usage. You want to access during the layer construction and use what you access priorly to construct other services. So you don't need the dependency that you use in construction to the usage. When instead build like a runtime of services and just use them in your app, in your normal effects, then this is very handy because you no longer have to separately access the service and then use it. But there are cases when you want just to separate it and you first access the tag and then use that. Those are for cases where you don't want. The other small point is the next in between is a function. So if you check that signature, it's gonna return an effect which to that function because functions are also constants. But the second one is probably what you want. We fetch the return types instead of.
So I think something really great there is talking about separating the kind of accessing from the context versus the usage. And that is where, to answer your question, I believe, of when kind of calling effect.context is useful in the real world, is exactly that case where we want to separate the kind of access from the usage. So what that looks like is, if you'll notice from here, calling const service equals, I cannot type. If you notice that this returns the service synchronously, it doesn't return as an effect. And so you can think of kind of yielding the tag as actually the same thing as this kind of service members, right? It's doing two things at once. It's getting the service or it's a little bit different, but I think what I'm trying to say is, yeah, so getting and using. The reason that context is useful to get is because getting from the context is synchronous. And the reason when that is useful is because interrupting with non-effect code. So the example Mike gave me is, let's say inside your effect, you have non-effect code, or code that basically can't be effects. It has to be purely synchronous. So you can effectfully get the context with effect.context outside of that purely synchronous code. And then inside the purely synchronous code, then you can use context.get to synchronously get from the context. Where if you didn't use that, the only other option is yielding the tag, which is an effect, right? But by using effect.context, we first effectfully get the context, and then we can give that to some code that cannot be effectful, and it can synchronously get items from the context. Bit of an advanced use case. I would say if you use that, that's probably pretty cool. I have definitely never used that, but it's kind of interesting to think about. I'm a bit conflicted on whether to do the error exercises because they are a bit on the hard side. And we are dangerously behind schedule. It's almost 12:30, which is when the second session is supposed to stop. So we can, I think, we're going to eat lunch. But when we come back, like I said, we're a little bit behind schedule, but that's totally okay. So we have a couple other topics to cover in this kind of first core part. And I think we will do the exercises just so I can kind of walk you guys through the solutions. And at this rate, we are probably not going to get to very much of the second or third parts, but that is totally okay. And so I hope everyone is learning a lot. And if you have any questions during lunch, please talk to me. And we have 90 minutes. So we're going to come back at 2. And yeah, thank you. All right, welcome back, everyone. I think let's go over quickly just a bit of an updated schedule. So I think what we're going to do is we're going to finish going through the rest of part 1. So we have resource management, and then we're going to do the resource exercises. Then we have the data types. We're going to do the data exercises, and then we're going to end with the error exercises, because I think they kind of have some stuff that we're going to learn, and then we're going to use in those. And then we should have time to get through all of part 2, and I think that will be very helpful to kind of see the effect in use, and then we'll end the day with some of the stuff from part 4, right? So let's just pick back up with, so we finished context management, and we finished the exercises for that. The one thing, there was a question kind of during our break about if you have, so you can have different implementations for a service, right? So the example was you have a database service, and you have like the live database and a fallback database. And so the question was about with memoization, if we provide kind of 2 versions of a service, how does Effect kind of know which one, like how do we kind of determine if it's the same value? And so the answer is that you should never be providing 2 different layers for the same service with 2 different values, right? And because those should actually be 2 different services, right? So if you have, and you can have 2 services with the same kind of interface, right? Because the interface is separate from the identifier. And so in this case, right, the solution is not to have 2 different implementations of the one database service. It's to have a kind of first database service and a fallback database service with the same type, and then you can provide implementations for both of those services. And then if you wanted to, you can make like another kind of parent database service that depends on both of those database services, and then kind of internally does the fallback, right? But I think that's an important kind of thing to take away, where if you have a service, the layers are kind of separate layers, right? Like you have your live layer and you have your test layer, and those represent the live versus the test implementation of that service. And you should only provide that layer, like you should only use one version of a service in your app. So either you're providing the test layer or you're providing the live layer, but you should not provide both. So hopefully that makes sense. So moving on to resource management. And so resource management is all about this special data type called scope. And so scope is something that is going to be a service, but it's kind of a special service. It's not really a service in the way that all of the other services we've looked at so far are. And so scope is all about managing resources. So those are things with a lifetime, or basically things that have some kind of finalizer, right? So if we think about opening a file, closing a file, right? And so what a scope defines is a scope basically has a series of functions called finalizers, and when the scope is closed, all those finalizer functions are going to run. And the way this kind of presents itself is by a scope type appearing as a service. But it's, again, different from other services because we're not providing an implementation for the scope, right? The scope already exists. When we kind of when we define finalizers, which we'll look at how to do in a sec, that creates the scope. And so it's actually just kind of a convenient way to use the service kind of interface that we're using for other things to define resources. So when we use something resourceful, so like we open a file, and I'll show some examples of this in a sec. When we use a file, that is going to have an effect that requires a scope. And where we provide the scope kind of determines where that scope ends. And so I'm going to go through some examples now, and that might be a lot. And so the scope, just kind of like how context is just like a value you can work with, a scope is just a value. So we can make a scope, and we can add finalizers. And so these are just effects that when we close the scope, it's going to go through all of its finalizers and run all those finalizers. And so the first kind of way to work with scope is if you have something that only has a release phase. So if you have a file, there's like an acquire phase and a release phase, opening the file, closing the file. So if we can use this effect called effect.addFinalizer. And this is going to return an effect that requires this scope type. And so what this is saying is I have some kind of finalizer. Like this effect does something, and it has a finalizer. And the scope appearing is saying, I need you to tell me when I should run that finalizer, right? Because just based off this effect, right, when do we run this finalizer? Do we run it after the effect finishes? If we're composing it with other effects, where does that kind of scope get closed? And so just like with other services, if we try to run this, it's going to say, right, scope is not assignable to type never. And so instead of providing the scope service, we have this special function called effect.scoped. And effect.scope is going to remove the scope from the service type parameter. And what it's going to do is define the boundary of that scope. So this is going to say, do this effect. And then after you do this effect, where effect.scope gets called, run all the finalizers of the current scope, right? Close the scope. So then the scope is removed. So when we run this, it's going to run first, and then it's going to close the scope, and it's going to run last, which, let's see. There, up here. So first, or there's some other stuff going on. I should have commented them out, but conceptually, all right, this is declaring the finalizer, so this is going to run first. When the scope is closed, this is going to run. And so here we have a function where we call effect.addFinalizer, and then we call scoped before we yield it, right? And so what this is going to do is, because where we call effect.scope defines the scope, this creates an effect within a scope, with a scope. This immediately closes the scope, and so this is going to log right away, and then this is going to log, right? So we have a bunch of functions to kind of create. Yeah, we have a bunch of functions to create scoped resources. So the most basic one of these is called acquire release. So acquire release takes two functions. So one function is going to create the resource, and the release function is going to release the resource. This is like a subscribe, unsubscribe function. So here our acquire function is going to open a file. So it's going to use fs from node, and it's going to try promise on fs.open, and then it's going to log out file opened. And then release is going to take the file handle and call file.close and then log file closed. And so when we give both of these functions to acquire release, we get a function that gives us the file handle, but also requires the scope. And so that way, when we use this file, and so here we can see this use file function. So this is going to take the file handle. So we can get our file, right? This is this. And we're piping it into effect.flatMap. And so after we kind of evaluate that effect, right, we get the handle, and then we use the file. And so this is going to be void, because using the file, this returns void, because console.log returns void. And so this is saying, right, this still has the scope, but when we provide effect.scoped, after we use the file, then the file gets closed. So I can, yes?
So effect scope, basically build.
Yes. Oh, yes, I'm sorry. So the question is, like, what does effect.scope do? And so effect.scope closes the scope, and at the same time, it removes the scope service from the dependencies type parameter, right? And so another way to kind of work with scoped resources, if we kind of know the exact kind of place, if we're just using it in one function, is this acquire, use, release. And so acquire, use, release, we're able to avoid working with like having to manually close the scope, because we very explicitly say where we're using the resource. So use, we're saying the only place we have access to the resource is within this use function. So we don't need to close the scope, because after this use function is finished, then we're releasing it. And so this is going to return whatever use returns. There is one kind of footgun to this, which is that if you close the scope too early, you still get the thing that has already been closed. So for example, here, this example is OK. So we're getting the file. And so this, remember, file returns a file handle but requires a scope. And so only after we use the scope, then we're calling effect.scoped. But if we close the scope before we use the file, there's only so much effect can do on a type level to prevent you from kind of misusing the lifetime of resources, right? And so in this case, this is going to close the file immediately, but we're still going to get the file handle back, but that file has already been closed, so that can lead to errors. So this can help you, yeah. Does anyone have any questions about scopes? So we're going to look at some exercises now. So the first one, I think we all should be able to do, which is great. So we have a mock file class, and the mock file class has a close static function, or a open static function, and a close method. And your job is to create a function that takes a file descriptor and returns an effect that returns a number. This should be void, I think. You can make that void. And basically, we want an effect that represents the opening and the closing of that file. And the way this works, by the way, is so there's this log test method. And so when you run the test with this like test run method, it's going to keep track of things you log with this log test. So what we're expecting here is when you open the file, this is going to run, and it's going to open 1. And then when you open the second file down here, open 2 is going to get logged. And then when you hopefully, when this scope gets closed down here, close 2 is going to get logged, and then close 1 is going to get logged. So your job is to create this file function, which is going to create an effect that opens the file and then closes the file when the scope is closed. And by the way, I believe the correct type for the effect should be the mock file. Like you should get the instance of the mock file that's returned from the open function. Yeah. That is correct. Thank you. So yeah, so the way this log test function works is it requires this test, which I think, so this t.t, I don't even think I exported. Oh, I did. Okay. No, I don't. All right, so here's one solution. So this is going to require the scope because of the finalizer here, right? So first we're opening the file, and that's actually what we're returning. But before we return it, we're adding this finalizer where we close it, right? And so this is going to return an effect that returns the file, but requires the scope because of the finalizer. And this is basically what the function that what acquire release does under the hood, right? So the alternative is we can kind of doing this in one step is acquire release, and we open the file, and then we close the file. Does anyone have any questions about that? And the other solution was here, right? So this is like the manual way of doing acquire release, where you kind of do the require function, and then that's what you end up returning. But before you return, you do the release function in a finalizer. And so that's what acquire release is kind of doing in one step. Yes, Mike?
Saying there's a minor difference between the two solutions. The one, if you go back to the acquire release one.
Copy this over.
So here, okay, thank you. So in the second solution, the mock file.open will run uninterruptible. So if that was an asynchronous operation, now opening a file is probably synchronous and pretty fast, so you wouldn't get interrupted in between. But generally speaking, when you acquire resources, you want the acquisition to be non-interruptible. The acquire release runs both the acquisition and the finalization in non-interruptible regions, so they cannot be interrupted. The solution number one, if you interrupt it while opening the file, you may risk of leaking open handle or stuff like that. So it's a little bit more tedious if you want to do it manually in a non-interruptible way, which is why we have the acquire release.
So what Mike is talking about, we will talk about near the very, very end, but in effect, there's this concept of interruption, which is, again, we're going to get we're going to get to it near the end. But there's this idea that we can interrupt things. And usually when we're acquiring a resource or when we're releasing a resource, that's like the worst time for interruption, right? Like we want to make sure that our resources are like very kind of clearly, like all the acquire operations go through, and we never want to like stop a release operation. And so we'll talk about interruptions in a bit, but you can, and again, you can manually do that, but acquire release is very convenient, and it's going to make sure that both the acquire phase and the release phase are wrapped in those uninterruptible things, which I know that's a lot kind of throwing at you, but we will get to that a bit. The next exercise, I'm actually not going to have you do because I kind of structured it where there's like, I haven't taught you how to do it, and there's only one way to do it. So I'm just going to explain what's happening. And so the crux of the problem is, if you notice, right, this effect returns a scope, or requires a scope. This effect requires a scope. And this effect, if we get rid of this, this effect doesn't require like scope 1 and scope 2. It just requires the one scope, right? The scopes have kind of merged magically somehow, which usually is kind of useful, right? If we have a couple things all in the same function, they can all share the same scope implicitly, and then we can close all of them at one time. But there might be a case where like we want to close the first file before the second file, right? So by default, they kind of get closed in the reverse order they were added. But let's say we want to manually prevent those scopes from merging. And so there is a way to do this. And the way to do it is using this function called scope.extend. So we can manually make a scope, which again is just, it's this data type that contains a series of finalizers. So we can manually create a scope, and we can create two scopes. And then when we call scope.extend, what we're saying is take this effect and take all of its finalizers and put them into this other scope's finalizers. And so in that way, what this is doing is removing the scope from this, because we're saying take this scope and put it into scope 1. And here we're saying take this scope and put it into scope 2. And then we can manually close with scope.close each of those scopes. So this is like actually fairly low level. Like I can't think of a lot of times you would need to do this. I mean, there are like a ton of valid use cases, but it is kind of interesting to see how to prevent those scopes from merging, and also to know that they kind of merge automatically. So I have a recap slide about this. So resource management, right? A scope contains finalizers that run when the scope is closed. When an effect requires a scope, it's saying, I have some resources, I have some finalizers, I need you to tell me when to run those finalizers. And using effect.scoped to provide the scope is indicating that boundary, right? Indicating where that scope needs to be closed. And then if we want to create scoped resources, there's this helper function called acquire release, where we can define an acquire function, define a release function, and it's going to make an effect that's automatically scoped for us. Does anyone have any questions about this? Okay. The next thing we're going to look at is effect data types. So there's a lot of data types in effect, and outside of just the effect type. Like the effect is its own type, but usually these types are used as data. We're kind of describing computations, right? Not using as data. So the first type is option. If you've worked in any kind of functional something before, this should be pretty familiar. And so an option is a union of either some or none, right? So we either have some value or we don't have a value, and the option describes both of those possibilities. And so there's an option type in effect, and all these functions are coming from the option module, so you import option from effect. And so we can create a none with option.none, and create a sum with option.sum. And then also option has a lot of ways to kind of convert in and out of knowable values. So we can create an option from a knowable value, and then we'll see in a second a lot of ways to kind of get the values out of options. Here's some operations on options. So there's a isSum, right? So and there's also an isNone. So will return a Boolean if it's some or none. And actually, if you want to do this on your own, I mean, this is like kind of to see how option works, right? Like there's just a tag field, and tag is you can see it's either none or some. And so option is quite simple, right? Like either it has a tag none, and there's no value, or it has a tag some, and there's a value property with the thing. Just like how we can map on an effect, we can map on an option. And so what this is doing is it's saying if it's none, right? Just like if there's like if we have an effect that's a failure, if it's a failure, obviously we can't map on the failure. Just like with that with option, if it's a none, we can't map on the option. But if there's a value, we can modify the value with this function. There's also flat map, right, where we're returning an option from the map function. There's match, where we can do something based on the result of either none or some. And then to get the value out of an option, we can use get or else, which is going to provide a fallback value. We can use get or throw, which is going to throw. We can use get or null, which is going to return either the thing or a null, and get or undefined. And so this is a kind of a way to describe, right, either having something or nothing that is a bit more clear, and also kind of the benefits you get over just having like t or null or t or undefined is that you have a lot of functions to work with those values, right? Like if you had t or null and you wanted to map on it, you'd first have to check if it's not null or use like the kind of optional. There's a couple ways to do that, but this is how it's a bit more, I would say, clear. And there's a lot of combinators to work with that. So just like option is either, right? Again, very, very common thing. And so option you can actually think of as either, and either is just two things. There's a left or a right. And option you can think of as either where one of the things is basically nothing. And so here we have, we can describe like an either that's either a number or a string. The one thing to know about either is that the two sides of the either are described as right and left. So there's the right side and the left side. Those are the two kind of members of the union. The one thing that is confusing is that right is actually the left type parameter. So the right is the number, and the left is the string. And so there's a couple reasons for this, mainly because people felt like, so in effect, right, the value is the first thing. There's a couple other types where the first thing is like the most important. And even though either isn't like biased to either side, there's no like correct side to either, where in an effect, like there's a success and a failure, left and right, there's really no difference, but people felt like right was like the success and left was the error. So right comes first. But just like with you have is some and is none, there's an is right, there's an is left. You can map left, just like with like map error and effect. You can map on both. You can flat map, you can match. Lots of things you can do with either. A really key distinction here is either kind of looks eerily similar to effect, right? In effect, we have success and failure, and either we have right and left. So there's a lot of functions where maybe you could return an either or you could return an effect, right? If you're doing something that involves side effects, you should always return an effect, always return an effect. But let's say you're doing something kind of purely synchronous that's only operating on data, then it's maybe a bit more hard to say. I think the answer I've been given before is you'll never be wrong just using effect everywhere. Even if you're not doing side effects, you can use effects everywhere, right? And then it's even more clear, right? With right or left, again, even though right is kind of like people say it's like the success type, there's kind of no kind of built-in definition, where success with effect is very clear. A success is either, an effect is either a success or a failure. And so someone had kind of come up to me over the break and talked about how if you're coming from kind of other functional libraries, you may be used to kind of, you can have like an either and you can have an IO either. So that describes an IO operation that can succeed or fail. Where in effect, those are kind of all kind of merged into one. And so I would say either is kind of most useful for describing data. If you have data that's something or nothing, you can use an either. If you have like some kind of computation that can succeed or fail, that's where you use effect. The other, and then the one other distinction is that effects are lazy and options or either are eager. So when we have effect and then effect.map and effect.flatmap, all those are going to become one effect, and like they're kind of lazy, right? We have to execute that effect to run all those through. But all operations on options or either are synchronous. They just happen, right? When you call option.map, it executes immediately. So here we have a side effect. It's a side effect, so it's going to take a number and log the side effect. So if we map with the side effect, the log's not going to run, right? Because we have to run the effect to trigger the side effect. But with either, the side effect happens immediately because either and option are eager. The other use is interrupting with non-effect code. Because option and either are purely synchronous, they're a really great way to kind of also get that like either success or error data type that you don't have to wrap everything in an effect. So if you're working with non-effect code, you can kind of use eithers in that way. So how do we convert from one to the other? Mainly from options and eithers to effects. And so I talked about tags, right? Tags are a subtype of effect. So we can use them in any effect concept, in any effect context, as if they were an effect. And so in the same way, you can use an option and you can use an either as if it were an effect. And how that maps is if you have an option that's basically equivalent to an effect that is either succeeds with the value or fails with this no such element exception. And if you have an either, the either maps to an effect where the type parameters are flipped. So here we have flat map, right? Effect.flatMap, and we're flat mapping on an option. And it actually just works. It actually just works. And you can also see that we're flat mapping not to an effect, but to an either. And even though it's an either, it's not an effect, it just works, right? Now these can probably be overused. Again, if you have a computation, prescribe it in an effect. But this is a convenient way to convert from options or convert from eithers into effects. Next, we kind of already looked at this, but we have exit. And so as I mentioned earlier, exit is equivalent to an either or a cause E. And we can get an exit from the run sync exit. And something you'll also notice is if we go back to resource management, is when we call a finalizer, I believe in here, we get an exit. And so what this is saying is all effects, when they kind of finish executing, they have an exit, right? The outcome of that program. And so what this finalizer allows us to do is to determine what to kind of do in the finalizer based on the exit of the effect where the scope is closed. And so exit, right, we can match on the exit, and it's a union of either a failure of a cause or the success value of just the value. And so the cause, as again we looked at earlier, kind of describes all the possible ways a computation can fail, right? So more than just pure failure, there's lots of other kind of more advanced failure cases, right? Is this a known failure? Is this a defect, right? An unexpected failure? Was the effect interrupted, right? Is that considered a failure? Is it not considered a failure, right? So we have it as a separate option. And then did errors happen sequentially or in parallel? And so the cause can encode all of those possible scenarios. The next data type we have is duration. And so duration is kind of a type that represents a time duration. And you can construct it from milliseconds, from seconds, 0, infinity. I think there's days as well. You can decode from this kind of string 7 hours. And then you can get these out as milliseconds or seconds. And there's a couple other constructors, a couple other destructors. But it's a way to kind of, rather than kind of taking in a number in your API and being like, is that milliseconds, is that seconds, you can take in a duration. And the user of that API can kind of provide whatever duration they want from whatever units they want, and you can get out whatever units you want. And of course, there's a lot of functions on that, less than, greater than, some, times. And those will all kind of modify the kind of internal value of a duration. So the next data structures we're going to look at are your more like typical data structures. So we have a linked list, we have a hash map, we have a hash set, there's a red-black tree, there's a couple of these. And these are all, unlike a JavaScript map or a JavaScript set, which is mutable, these are all functional and they're all immutable. So what that means is basically every operation is going to be a function and not a method. And every time you operate on one of these data sets, you get back a new copy of that data. So if you've never worked with this before, right, if we have a hash map, we have an empty hash map, and we assign that to a variable, and then we say hashmap.set, the key and the value, we're going to get back a new hash map. The original hash map will still be empty, right? So the next data type, and I'm not going to go into these too much. I think we'll look at one in one of the examples. But these are just to kind of let you know that they exist. The most common is probably hash map and hash set, which actually we'll come back to in a second. But the most common data type you're likely to run into is this thing called a chunk. And a chunk is very similar to an array, right? It's a kind of collection of elements that are ordered. And you can conceptually think of this as being equivalent to array, but there's a lot happening under the hood that is going to, it does some cool stuff. And so the reason is it's immutable like all the other data types. But the reason this is important is because when we append to a chunk, right? Instead of copying all the elements from the previous array and copying them into a new array, except with the element at the start, what it's going to do under the hood is basically create this new thing that has a pointer to the new element and a pointer to the previous elements. And so only when you kind of tell it, hey, I want the chunk as an array, it's going to go through its kind of internal structure that might be split up into a couple of things and copy all those elements to an array. But by default, there's a lot happening under the hood that makes this a bit more powerful than just a function, right? So it's not going to fully copy everything every time you mutate it. And so you can make a chunk, you can make a chunk from an iterable, you can append, you can drop, right? All very common array operations. But internally, the chunk is doing kind of different things. And so if you want it out as an array, you can call chunk.toReadOnlyArray. But there's also kind of built in, there's like a chunk.forEach, and there's a couple other methods built in. And so that way, even if it's kind of broken up in its internal structure, the chunk knows how to kind of go through that internal structure. So you don't have to copy everything to an array to kind of go through all the elements in the chunk. And so finally, are this thing called traits. And I put traits in kind of big quotes. And so the two traits effect has are equal and hash. And so they're very similar to kind of the iterator trait, again, big quotes, right? Where we can define our different data types to become iterators by giving them like the symbol.iterator key, and then it can return an iterator. And then we can use it in functions that take iterators, right? There's an iterator interface. And so just like that, effect has traits. And so equals works with a function called equals, and hash represents a function called hash. And so equals takes two things and compares them. It's going to return a Boolean, either true or false. And a hash is going to take a thing and return a number, right? That is some kind of hash of that thing. And so all types have a default implementation. So equals will always work with any type, hash will always work with any type, but you can provide custom implementations. And so where this comes into play is you can define, for example, deep equality, right? We can create a custom implementation of equals that doesn't just check referential equality, it checks deep equality. And I'll show you that in a sec. But where this becomes really useful is with normal sets in JavaScript, they only work off referential equality, right? So if we kind of make a chunk and we add another chunk, the size of this set will be 2, because we added 2 separate objects, right? The first chunk and then the second chunk, and these are 2 separate objects. But if we use the effect hash map and we add these 2 chunks, the size will actually be 1, because these chunks have a special equals implementation that makes them so when you use the effect equals, they're going to be true. And when you hash both of them, they're going to have the same hash. And so because that's the case, the effect hash map, which operates off the effect traits, is going to say, well, these are the same value, so I am not going to create obviously they go in the same spot in the hash. So to implement a trait, you implement it just like the iterable, right? So here we have a foo, and foo1, which just takes a number, and we have foo2. And foo2 implements the equals.equal trait and the hash.hash trait. And these are really just functions, right? So here's the equal interface, and it just has this equal symbol, and it takes a that and returns a Boolean. And so hash is the same, except it returns a number. And so how this looks like in practice is we define a function for the equals symbol, that returns a Boolean. So in this case, we're checking if the other thing is an instance of foo2 and if the numbers are the same, right? So kind of a deep equality check. And then hash is just going to return this hash.number function with this.x. And so when we do this, we can see that if we add, right, so we have foo2 where we've manually implemented these, and we have foo1 where we have not. And so if we add 2 foo1s and 2 foo2s, then the size is going to be 3, because the hash set is going to see these as distinct, and it's going to see these as the same. And with equals, we can call equals.equals. And so this is equals, like the equal module, right? We're importing equal from effect. And so we call equals.equals on the 2 foos, and these are different, but the ones where we manually defined the implementation, they're the same. So next is the data module. And so data module contains a number of functions that basically implement deep equality and hashing for you. So if you want to manually implement stuff, you can. And this is probably most useful if you have an equality check that only depends on some kind of, like you have a type with kind of multiple things within it, and maybe you only care if they're equal about 2 of them, right? And so what equal is going to do is define a kind of default implementation that by default is going to check deep equality. So all the things are equal to all the things. And so the first way, there's kind of, each of these ways has 2 ways. So the first way is with a class, where I talked about class, you can define a type and a value at the same time. And so there's a class way, and the non-class way, you have to define the type first, and then you define the value. So for data.case, we first define this type, and then we define the constructor, where we pass the type in, and then we get back this constructor, where we get back this value of the interface type, but this value has a special equals implementation and a special hash implementation for us, done for us. And if you're doing something that is tagged, which is quite common, you use data.tagged instead. And so I would say the much more common way of doing this is with classes, right? So we can create a kind of data.class here, and this is automatically going to implement the hash and the equality for us. And obviously with tagged class, the same thing, but automatically tagged with this string tag. And the other useful things about tags, or with classes, is if you want to define additional behavior at the same time, you can. And then there's this other function which a very common kind of thing in effect is to have unions of tagged data types, right? And so there's this function that kind of can create all of the constructor functions for a union of tagged data types at once, which can be useful. And the last thing is data.taggedError. And so data.taggedError is basically the same as these other functions we've looked at, but there's something special about this data type, which is that you can yield it just like an effect. So normally you'd have to wrap this in effect.fail to create a failure. But if you use data.taggedError, you can omit that effect.fail. It will automatically know that this is a failure. So now we're going to look at the exercises for data. And so the first one I have for you is to manually implement equals and hash. So I have a type, it has 3 fields, and your job is to implement the equals interface and implement the hash interface. And then I think we'll try to do both of these at the same time now. So the second exercise is to create a data type for a string that is guaranteed to be only ASCII. So I gave you a regex, and so however you want to do that, create some kind of function that takes in a string, make sure it's only ASCII, and then returns some kind of special type. And yeah, we'll take 5, 10. So the brand was actually what I had in mind. Now there are a couple, and the reason for that is, so does anyone not know what a brand is in TypeScript? Just raise your hand. Yes, okay, let's go over this. So we talked about, this whole module is about data, right? Creating our own data types. And so one option for this would be to kind of create maybe I think a class is a good way to do this. called ASCII string that has a constructor, and it takes a value string. Oh, I'm very sorry. I'm very sorry. There we go. Okay. So one way to do this is declaring a class, right? A class is a new data type. And so then in the constructor of that data type, we are kind of doing some validation logic. But the thing with classes is they're objects, right? And there is some overhead to creating an object, right? Like especially if this only exists as a wrapper to a string. It will never do anything more than a string. It is literally just a string that we have added some validation logic to. But we never want to confuse it with a string, right? An ASCII-only string is a completely kind of separate thing than a normal string. And so if we just do this, if we just say type ASCII string equals string, this is not the same. Even if we write a function that first validates something, we can pass this non-ASCII string into this ASCII string. And so the question then becomes, how can we make a type distinct from another type without creating a wrapper type? And so the solution to that is something called a brand, which is a useful TypeScript trick. And what a brand does is it allows us to kind of take primitive types. So a primitive type is like a string or a number or a Boolean. And take these types and separate them, where make an ASCII string separate from a normal string. Make it something new. And so the way you do that is you add this thing called a brand. And so we're going to use the brand module from effect. And so we're going to say brand.brand. It's going to take a string, ASCII string. And you don't actually have to use the effect way. Like this is a useful thing to do, but you can actually, a lot of the times this is called brand ASCII string. But the idea is on a type level, this is now distinct from a string. Because even though this intersection is not actually possible to create a value, I mean, you could, but basically because a string doesn't have this brand property, it is now a separate type from a just base string. And so now you see we get this error, string is not assignable to ASCII string. And so in effect, there's this thing called a brand, where we can manually make this with brand.brand. And then we can write a function called validate ASCII. And this is going to return an ASCII string. And so then if we kind of validate ASCII hello, right? And then do this. Now, this should work, right? And so, again, the reason this is useful is we can create a new type that is distinct from some other primitive type, but without the overhead of creating a wrapper. And so effect gives you some nice ways to create brands. And so that's going to look like this, right? So the type brand has this brand.brand. And then there's two functions in the brand module. There's a function called brand.refined, and there's a function called brand.nominal. And so brand.nominal is going to return a function. And this function is like the constructor function. It takes in the previous type, just a string, and it gives you an ASCII string. And the reason for this is because, again, strings and ASCII strings are different. And to get an ASCII string, actually the only way to get an ASCII string is to manually cast the string to an ASCII string. And so nominal says that there's no kind of validation logic we want to do first. We just want to create an ASCII string from a string. But this brand function takes a validation function. And so that was my goal here, was to say, to kind of show this function and show you how you can create a new type that first is going to test the string against the regex, and otherwise you can map it to this brand error. And that way you can create these types. And you could, again, you could do this manually, but this is, Effect provides a way to do this. So this is what I did. So I think this was very similar to what you had done in the back, where first, right, we're checking. And so these are actually, there's no right way to do this, right? Like you could decide that I only am deciding these are equal if the IDs are equal. And maybe these checks are like expensive, but you know if the IDs are equal that these are the same. And so this is one way to check all of the items. But again, you can, how you define equals is up to you, and it can change per data type, right? And then for hash, so you could do something like you could return like this dot ID dot length plus this dot amount plus this dot time dot get time. But the hash module provides some functions that if you look at them, they basically do a bunch of math and kind of bit shifting and stuff. And so this is one option, right? Maybe this is a bad hash, maybe it's a good hash, we don't know. A probably better hash is doing this, where we use the functions from the hash module. And so first we hash.string, and then there's this hash.combine function, which takes two hashes and combines them. And so this is, again, one solution, but the whole idea of this is that you can implement however you want for your data type. Or I guess I did make the test cases so that they should be the same, but in theory, you could make them however you want. So the question was, this person is using this thing called Schema, which I'll talk about in a second, and they're kind of unclear kind of where, with all these different modules, what is like the right way to define our data types? Where should the types come from? Where should the values come from? What about all these different errors? And so on Schema, so Schema is something we're going to talk about, we're hopefully going to get to, and we will, is a effect first data validation library. So many of you are probably familiar with Zod. So Effect has its own version of Zod called Schema. There's some really, really cool things, which we will get to. It can kind of be confusing sometimes where the kind of definitions for your data should come from. So for example, you can define a schema, you can define a schema, like within the library schema, and then you can derive the type of that structure from the schema, and then you can create a data type of the same type, right? And so that might be one way to do it. There's also, within Schema, there is a way to create a class, which also creates a data type. And so there's a lot of ways. And I don't think there's like one good answer. I think it kind of depends on what you require. So if, I mean, this is, even without Effect, it's also, I think if you're using Zod, a lot of people like wonder, like, do I define my data types first and then create a Zod validator or some kind of schema for that type? Or do I make the validator and then derive the type of the data from that validator? And I don't think there is a good answer. I think when you're defining your own data types in your application, as like a default, I think you can't go wrong with just, I think classes are really convenient, but you don't have to use classes. But again, the thing that's convenient about classes is you're getting the type and the value in one place. And then if you want to use the data module, you don't have to, right? The data module is going to provide kind of implementations of these. So if you think, okay, I'm probably going to need a strict equal implementation, I'm going to need a hash implementation, then you can use the data module classes like this. I don't think that was a great answer, but I think the answer is basically it's complicated, and there's lots of different ways to do it. And yeah, I'm sorry, did that kind of get to what you were asking? Yeah, I'm sure Michael would have an interesting answer. As always, I think Morella had kind of talked about joining the Discord. If you guys do have questions on the Discord, people answer all the time. There's a beginners channel, there's a not beginners channel, but don't be scared to ask in the not beginners channel. There's channels for different modules. So if you have questions, even as simple as like, hey, like I have some type, how do I define this type? There's like 5 different ways you've told me to define types. So definitely feel free to ask in the Discord. So finally, on to the errors exercises. I have a couple things that I want to kind of hints I want to give you so that these are much more doable. And so the first one is, I'm going to talk about all of them, and then I'm going to give you a chance to do all of them, just because I want to kind of explain each one. So here we have an effect, and this one uses effect.suspend, which we haven't talked about yet. But effect.suspend is a way to, just like how in effect.sync, we're delaying the creation of the value until we run the effect. And so effect.suspend is the same, but instead of creating a value, we're creating an effect. So it's saying, it's basically creating an effect behind a thunk. So effect.suspend creates an effect from a thunk. So we're lazily creating an effect. And there's a couple reasons why you might want to do that. This is one of them. There's probably better ways to write this effect, but this is a way. So we have a variable I that we are incrementing every time we call this effect. And if it's 100, then we're going to succeed. Otherwise, we're going to fail. And so the challenge is to find a way to basically keep running this effect, like repeating this effect until it doesn't fail. And so the hint I'm going to give you is there's this function called effect.retry. And effect.retry is going to kind of do what it says on the tin, which is retry. And so we can put eventually succeeds. And then I'm going to give you a chance to take a look at the type of this kind of second argument, and you can try to figure out a way to have this keep going. Now, the second one is going to utilize effect.all. So as I talked about, one of the things with effect.all is that when you run 10 effects, if the first effect fails, the other ones aren't even going to run because the entire operation will fail. And so the challenge for you is to, instead of short-circuiting, right, instead of stopping on that first error, to collect all of the errors and fail with an array of them. And so the way you're probably going to want to do that is there's in effect.all, there's a second argument, and you can give it a mode. And the mode for this one you're going to want to use is validate. So I'll let you look at what validate does, and then try to get the array of errors from that. And then finally, for this last one, instead of just having an array of errors, you're going to run all the effects, get an array of all the successes and all of the errors. And for this one, you're going to want to use mode either. And so just like with validate, I'll give you a chance to take a look at what that does to the type signature, and then try to kind of modify the result. I'm sorry to cut off people's work, but we're basically at the end of this session. So we're going to go over this and then take a short break. Was anyone able, let me unfreeze this, was anyone able to get 1? Okay, who wants to share their solution? Yes? Okay, that is one solution. And we'll talk about schedule in a second. The other solution that's maybe a bit simpler is you can have while and then true. And so to start, I know I didn't necessarily introduce this maybe the most formally, but effect.retry, there's 2 functions that kind of are the core functions of repeating effects. So there's effect.repeat, and there's effect.retry. And so they're kind of opposites in that effect.repeat is going to repeat an effect while it succeeds, and effect.retry is going to repeat an effect while it fails, right? So we're retrying an effect if it fails, otherwise we're repeating it if it succeeds. And so here we have an effect that's going to fail the first 99 times we run it, and it's going to succeed the 100th time. And so we can use retry, and while true is basically just going to retry it forever. And then on the 100th time, this is finally going to succeed. And so this is one of the first solutions. The other one is there's some other options here, right? We can say times. We could say infinity. If you put anything over 100, it'd also work. And then the other option is there's this thing in effect, which I don't think we'll be able to cover too much, But there is, I wrote a lot about it, so if you want to, like when we go home, there's a whole schedule file. But the schedule is basically a data type that kind of describes the repetition of an effect. And so there's a schedule called forever, which is just going to repeat forever. And so this is another solution. Was anyone able to get exercise 2? Okay. Do you want to share? Yes. So what does validate do? So validate, if you look at the result, if we get rid of this for a second. So validate returns either, so right, this is an array of effects, number, succeed with number, fail with string. And so this is going to turn this from a, if we don't have it, right, it's going to be it's either going to succeed with the array of the successes or the first failure. And so what validate does is it's saying either all of the successes or all of the errors. And so the reason that the errors are an option of the error type is because some of them might still succeed, right? So let's say the first succeeds and the rest fail. Then the first one is going to be a none, and the rest are going to be the option sum of all of the error. So it's representing all in the case that any of them fail, is representing either the error if it exists, or it doesn't because that effect succeeded for all of the effects that we run. And so then we can use map error to kind of modify that error type, which again is an option of a string. And we can filter is sum, right? Because we have either sum of the string or none. And so then once we know that it's sum, we can use .value to get at the value. So this is kind of combining some of the data stuff we looked at. And so the third one is also going to kind of look at the data stuff because the either mode is going to return either. So this is basically equivalent to before you pass it to effect.all, mapping with the effect.either function. And was anyone able to get this one? Yes, so the solution to this one is actually quite similar to the previous one, where basically we're mapping on the result and we're filtering based on either.isRight or either.isLeft. Anyone have any questions about this before we take a break? All right. Yes. Yes. So I think, yes. So the question is, if you do this, then this is typed as some string. But instead, if you do this in the kind of non-point free style, where we take kind of whatever this is, and we option.isSum on this, then this is no longer typed to sum, it's typed as option. And the reason for that is because this function is kind of manually typed as self_is_string. And so if we type this as this is option.sum string, you'll notice that this still works. And so this is basically just a TypeScript limitation. But I imagine that, so first of all, that cast is a safe cast, right? Because you just checked. So that what the cast I'm talking about is if you do this, casting this as as option sum of string. And so that might be a case where that cast is safe because you just checked. There probably are better ways to do this that might get the types right. But yeah, does that answer your question? And actually, there's a TypeScript PR that's very recent that the goal of the PR is to have TypeScript automatically infer type guards. So if that went through, this would work, but we'll see. So we're going to take a break, and we're going to come back in, say, 10 minutes, so 3:40, and finish off here. The thing I want to do right now is go through kind of how the rest of the content is structured that we're not going to get into, because I want to make sure, while we have time, to do my best to kind of explain how you can best take advantage of all the content that I spent a lot of time on, but in hindsight, probably I think would have realized we might have gone a bit slower. But that's OK, because now it's all for you at home. So these next two parts, the way they're structured is we basically, the first one is the CLI, the second one is a server, there's a chat server that uses WebSockets. And so we kind of incrementally rewrite them to effect. And in the breakpoints folder, there's a changes file, which describes all of the different steps along the way. And so each step, there's dipping our toes in, adding type errors, adding type dependencies. And then each folder in here is the version of the app at each step. And so you can go through and look at the one step and then go in the changelog and see what's changed and kind of see the difference. And then also in the project folder, which was where you can kind of, if you want to do the rewrite yourself, this is the first breakpoint. There's also a after the workshop, which kind of assuming we had got to it, there's a bunch of features you can add. So I would say this is still something you can do. And I think the usefulness is, even if you kind of don't do the rewrite yourself, I think definitely look through the different stages. And then you can kind of go through, look at the final stage and do your best to understand it. And then I still think these would be great exercises. There's a bunch of features that you can try to add to the final stage of the rewrite. And so these are all things you can try to do. And so in part 2, there's that. In part 3, there's that. And then also all the new modules that I use, there's these snippets files for all of them. So for schema, for match, for schedule, for config, there's files with examples and explanation. And all the explanation, there's explanation and comments. And so there's some docs pages for some of these, most of these. And there's also all of these you can go through. And there's also a couple exercises that you can go through. And so all of that you can go over. And like I said, part 3, the one thing to know about part 3 is there's a client and a server. So the thing I rewrite is the server, but to use the client I wrote in effect, and that's in the final breakpoint in the client folder. And so there's a special script to run that, which is bun run, and it's 3 project C. And so that's going to run the project. And so if you want to kind of test the server using the client, that's how you can run the client. And the same thing, there's a bunch of breakpoints, and there's a changelog, and there's stuff features for you to try to add. I think these would all be a very good challenge. And then also, if we don't get to any of this stuff, again, all of this is all here. There's tons and tons of comments all explaining it all. And of course, the slides are all available. Those are recap stuff. And then the one final thing is there's this cheat sheet.markdown file. And this is basically a cheat sheet for most of the stuff we ended up going over. So basically all of the construction, the running, the pipelines, error handling, context management, data is all going to be in this cheat sheet here, which is in Markdown. So hopefully that's useful to you. So what I want to do with our time left is we have a couple options. The one thing I do want to definitely do is talk about schema. And then with the time left, we can either talk about, so there's like 3 options. So one is we start the rewrite of the CLI, and we don't really finish. The second option is we don't really rewrite the CLI as much as we look at how I rewrote it. And so I say, like, here's the start, here's the end, here's what I did. And then the final option is concurrency is a really big, that affects concurrency model. There's this thing called Fibers, which you might have heard of. And so I can talk for a little bit about Fibers. And that's probably more advanced, but it is also very interesting. So we can kind of decide what we want to do there after schema. And the reason I want to talk about schema is because schema is really cool even if you're not using effect. So you can use schema in effect, it works really well, but you don't have to use effect to use schema. And so I mentioned earlier, but schema is a data validation library, just like Zod, right? So we have some type that is unknown, and we get out the type of the schema we declare. But where schema becomes really, really powerful is that it describes 2-way transformations. So most kind of schema libraries like Zod, you can define a 1-way transformation, right? So you can define a schema that kind of asserts some types and then operates on those types, right? Like within Zod, there's like z.string, and then you can, I think it's .transform, and you can kind of transform the number kind of like a map function, right? And what's powerful about schema is it's two ways. So a schema is generic over 3 parameters, an A, an I, and an R. And so the R is a requirements, just like an effect, and that's because the transformations can be effectful. But like I said, imagine effect doesn't exist. Imagine there's only 2. And so what a schema with these two type parameters can describe is asserting that a type of unknown is the first type parameter, the type of the first type parameter. It can assert that a type unknown is the type of the second type parameter, and it can describe transforming between the 2 types. And so this is really, really powerful because this is a really important concept in kind of sending things over the network, right? We have this like serialization and deserialization, right? And so JSON parse, JSON stringify are very kind of simplistic ways to do this, but there's all kinds of types that cannot be very simply stringified and parsed, right? So like dates, the date object in JavaScript, right? You can't JSON stringify and JSON parse it. And so that's where these transformations can become really, really important because we can define a data type and we can define a schema of how to encode that type to a string and how to decode that type from a string. And it doesn't have to be a string. We can decode and encode from any type to any type. And so that's why schema is so, so, so powerful. And so quickly to tie back to your question about how should I make my data types, I talked to Mike. And what Mike said was if you have a data type that you, at any point, basically anticipating wanting to serialize it, then you should create it in schema. You should define it as a schema. And because that will allow you to very easily define the serialization and deserialization for that type. And the way you probably will end up doing that is there's a schema.class, which I actually don't cover. But the schema docs are super, super, there's a big README. If you go to the schema repo, the README is massive. It is crazy. This library does so many things. But the schema has a class that allows you to like define data types and the schema in one place. We're just going to look at creating schemas and using them. And so also, the second type parameter by default is equal to the first type parameter. And this is because not all like types need to be transformed, right? Like a schema that just validates that something is a string, there is no transformation there. It's a string. And so if both of these types are the same, obviously there's no real transformation between the same type. It's the same thing. And so let's look at this first schema. So schema.string. And by the way, you import schema from a different package. It's not located in the same package as effect. It might at some point, but I'm not sure if it will. And the way you import it is this namespace import. So you import star as schema from @effect/schema/schema. And the other thing you might see is aliasing this as s instead of schema, but we import it from a different place. So schema.string is a schema that, again, string. So this is a schema that validates that something is a string. And schema.number, this is a schema that validates from a number to, or that something is a number. So here we can look at kind of the most basic transform. So in transform, it takes 4 arguments. It takes a schema for the type that you're transforming from. It takes a schema for the type that you're transforming into. And it takes a function to convert from the type of the first to the second, and the second to the first, right? And the reason that you need both schemas, the input type and the output type, is because we'll see in a second, but basically there are a couple functions that you can use with this schema. And the first, actually we'll get to that when we get to that, right? But this is how we can describe transformations by giving it a function from one to the other and one to from the other way around. Just like anything, right, these transforms can fail. And so we get this transform or fail function where this kind of looks very similar to effect. We have this like try and a try catch, and we return this parse result error. And so schema has its own error. It's called parse error. And I believe it's in its own module. So there's this whole parse, I think it's just in parse result. So parse result is its own module that kind of describes this parse error type. And there's a lot of cool stuff where parse errors, there's like a tree formatter and there's another formatter, but there's like the pretty printing, the errors get pretty printed by default, which is really cool. I think there's an example that shows that. And then of course, a really common pattern is deriving types from our schemas. So schema.schema.to is going to derive the first type, right? This is going to be number, and .from is going to get the second type, which is string. And so now let's look at how we can use these schemas. So I have two examples here. So we have takes number, which takes a number, takes string, which takes a string, and we have a string and a number and something that's unknown. And so the way the schema functions work is there's a couple of them, and here's an example. But we give our schema to one of these schema functions, and it returns back a function. And so I know I talked about with a lot of the effect functions, there's like the kind of two overloads where we can either pass the value first or just kind of leave it out and then we get back a function. But these you always get back a function. So if you want to call it, like we can declare this first as like its own function, right? Is number. And then use is number, right? This is a function. But if you want to call it just in one spot, this is a function, and then we call that function with unknown. So first is, and so is a type guard, right? So it says u is number. And so you can use it in an if statement to assert that unknown is a number. Something you'll notice about this is that there's no effect here, right? We're not yielding an effect. This is just synchronously returning a true or false. And so this is where I said you don't need to use effect to use schema, right? There's synchronous methods for all the schema methods. The one thing is, though, I talked about you can have effectful transformations. And so just like calling run sync on an asynchronous function, if you use one of these synchronous schema methods on a schema that has a effectful transformation, obviously there's no way to do that synchronously. So that's not possible. Next is schema.asserts. And so schema.asserts returns a function that asserts input is number, which basically means it's going to throw if input is not number. And so if we call that, then unknown is number. Next we have validate. And so validate is quite similar to is, except it's a effect. So here we're in an effect, and we can yield the result. And if it's true, we assert that unknown is a number. And you notice all of these operate on this first type parameter. So the to type parameter. And now for transformations. So to encode from A to I, so in this case that's from number to string, we use encode. And to go from I to A, so a string to a number, we use decode. And so there's a number of functions that kind of give you different outputs. So there's encode, encode sync, encode promise, encode option, encode either. And so encode gives you an effect, and encode sync just gives you the value synchronously, and promise gives you as a promise, option gives you as an option, and either gives you as an either. And so these are kind of useful for not throwing, right? So this encode sync, it's going to throw an error if the validation fails, where in this way you get the error back as a value. And obviously this would reject with the parse error instead of throwing. And then if we return it as an effect, the error is encoded within the effect. And so all these would work the other way too, right? So just like we can encode, we can decode. And then the one other thing is all of these have unknown versions. So there's encode unknown, and encode unknown sync, and encode unknown promise. And the decode unknown sync, which is 3 words, I know big words, but schema.decode unknown sync, this is basically equal to like zod.parse. This is your basic, I have unknown, synchronously tell me whether this is the right thing. And so the reason that's the case is first, we have to specify that it's synchronous, and then we're decoding, and what the unknown methods do is, if you notice, encode must take a number. And so this actually doesn't do validation, right? I think it actually does internally, but you can kind of conceptually think of it as not. And so what this is doing is it's only doing the transform. So in the transform, right, we had 4 things. We had the in schema, the out schema, the transform function 1, transform function 2. Encode is just calling that transform function. Decode is just calling that decode function. But when we decode unknown, what we're doing is taking unknown, using the schema that we pass to it to verify that it's the input and then transforming it, or verifying that's the output and then decoding it. And so if we look at this example, so this example uses, there's a lot of built-in schemas. So this schema is called date from string, and it's a schema that can decode a date to a string, or encode a date to a string and decode a string to a date. And so if we schema.encode sync with this date, it's going to give us a string. And if we schema.decode sync, it's going to give us back the date. The one question that I most had about schema was one-way transformations, right? Like sometimes we have transformations where there is no way to go back, right? We lose some information, it's not possible. And so the way to kind of handle those is in the function where you're going back, right, the decode function, you could just make this function always fail. So that's always going to result in a parse error because it's not possible. Like I said, the README for schema is very, 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 if I open this up, it is very robust and very, very long and very, very detailed. But the schema module is super, super powerful because it is a really powerful way of defining the shapes of our data, ensuring that our data are those shapes, and defining the transformations between different data types. And again, this is something that you can use even without effect, Does anyone have any questions on schema? I have some exercises for schema if we want to do them. Yeah, let's do it. I think this will be good. So the first exercise is I've created some types. And so you are going to do your best to create a schema that when we infer the type of the schema, it's going to equal this type. And so I'm going to kind of give you some hints. So there's a function called, I think it's schema.struct, and that's how you create an object. And obviously all the kind of core types are just the name, so s.number. Yeah, and it's aliased as s here. And then here you're probably going to want to use schema.union. There's schema.array. And again, everything's functions. There's no methods. So in Zod, you might be used to kind of calling methods on something, where in schema, we're calling functions. So you can either s.string.pipe s.array or s.array of s.string. And then the second test, if you're able to get to it, is kind of creating a schema that can transform from the URL type to a string and back and forth. I should have explained better, but the way to, or I'll wait until we go over all of them. But are we ready? I think we can come back. I want to have enough time to get to one other thing. So the solutions for this, and again, these are functions that I did not teach you, so it's okay if you didn't get them. But the first is with s.struct, so that's how we can kind of declare a object type. And there's Boolean, number, string, symbol. The next is s.literal. So there's two options. You can do s.union of multiple s.literals, but s.literal can also take multiple literals, and it will be a union of all of those. Then the next kind of really hard one is this template literal function, which has kind of questionable use, but it's cool that you can do it. And so this is going to construct a template literal of kind of combining other schemas and literal strings. And then to get a tuple, there's s.tuple. And then we can call s.array to get an array, s.keyOf to do keyOf. With D, if we want to have recursive schemas, we can use s.suspend. And so that's always a bit tricky one. The other thing is you have to manually declare the type of the schema in order for that to work. And then there is union and there is partial. So again, I didn't teach you any of this, but maybe you got a couple. And hopefully you kind of have a better understanding of how to construct schemas. So the next one, I don't even know how many of you got to it, but it's okay. So this is an example of how to transform from a string to a URL. So we take the string, and if we want to capture the error because the URL constructor throws if the string is not a valid URL, we can use this parse result.try, and we can catch the error and kind of remap it. And then otherwise, we can just call url.toString. And so then in schemas, there's schemas that filter, right? So s.filter creates a new schema that doesn't change the kind of types logic, but we can kind of filter like true or false on the values of the data, right? So this is going to also return the same types as this first URL from string, but it's going to make sure that the URL protocol is HTTPS. So another example, like you can have a string s.number, and then we can pipe it and filter to make sure the number is greater than 10. Okay? And then composing these two, we can compose schemas. And so if we have a schema from A to B and a schema from B to C, we can compose them to get a schema from A to C. So to end the day, I know I talked about a couple of our options. I think I am leaning towards the concurrency because I think we are not going to get very far into the rewrites, but the concurrency I think is decently complex, and the docs page on it is decent, but I think you can read the docs page and still be confused, and I think I'm going to do my best to give you the best possible explanation of something that I think is one of the scarier parts of effect. So I think that's what we're going to go with. So yeah, the way I want to start this out is usage frequency versus complexity. I would say what we're about to look at is maybe like here. What we're going to talk about is fibers and concurrency. And of course, concurrency is in all of our apps. We're doing web things, we're calling APIs, we're calling databases, right? Async await is everywhere. And so concurrency is something we think about fairly often. What we're going to look at is a little bit of how Effect handles concurrency under the scenes, which is more like here. But then I'm going to bring it back and show you kind of some APIs that bring concurrency, like high-level concurrency, that you're going to use all the time. So the first example I have is this snippet. And I kind of spoiled it here. But when you log this, or when you run this, nothing gets logged out. Does anyone know why? Yes, the event loop is blocked. So we create this interval, and you would expect that the interval is going to go off. But the way JavaScript works is this while true keeps the main thread kind of spinning, and these timeouts keep piling up, and they're waiting, but they can never go through because the while true never ends. And so I have this next example, which is basically the same thing in effect. It's a little bit different. So instead of the set interval, we have this console.log, and instead of set timeout, we're going to repeat it, and then we're going to use this function, which I'm not going to actually say what it does just yet. It's called effect.fork. And then we're going to call that, so that's setting up this timeout. And so if we don't have this at all, like imagine this is not there, this is just going to log on an interval. And then if we add in this while true, which is just going to increment the I, it actually works. And so I can try and show that here. Right, so here's the first example. If we do this and we run, it's going to be 4E1, 4S1. This is not going to work. But if we run this effect, even though we have this while true loop, it's going to start logging. Something interesting is it doesn't log every 250 milliseconds. It actually takes a bit longer. And we'll talk about why in a bit. But the fact that it logs at all kind of tells us that there's something else going on here, right? Like no longer is the main thread kind of spinning in a loop while these other things are piling up. And so Effect is kind of doing quite a lot behind the scenes. And so there's this kind of concept of cooperative multitasking versus preemptive multitasking. And these are kind of big words and big concepts. And you might not have run into these before. But cooperative multitasking is how JavaScript's event loop works. And so what this is doing is the reason cooperative is because we basically say we have like different concurrent tasks. Like let's say we have two tasks and they're both concurrent. And so what cooperative means is that one task has to cooperate. It has to kind of give up. It has to either stop or it has to say, I'm done for now. kind of do something else, right? Like I'm cooperating and I'm helping out. And so that's how JavaScript works, right? We have two ways a task can end. Either the stack can clear, and so what's currently running can finish, or we can call await. And what await is going to do is it's going to yield, right? It's going to basically give up and cooperate and give control to something else. And so that's, yep. Tasks are just a callback in a queue, right? Like when we call promise.then, we are storing a callback, and when the event loop kind of finishes, we're calling all of the callbacks. And so this was kind of the model, like the kind of concept behind Node.js, right, was we can have concurrency for very cheap because we can literally just store a pointer to these callbacks and then just call them when the main thread finishes. And so the opposite of this is preemptive multitasking. And this is how operating systems work. And so instead of giving up control themselves, there's some kind of external thing. And so you can think of this like in your like on an operating system level, right? We have processes that run, or applications, and they don't really yield. They just run, and our operating system and our CPU will kind of stop them, and it will externally kind of preemptively stop them before they even kind of finish or yield. And so tasks run in this model as if they're the only thing running. So they act like there's nothing else running, and the reason we can do that is because the task itself doesn't think about the concurrency. It just thinks about what it's doing. And there's something else, some kind of like scheduler responsible for switching between tasks. Yes. And tasks can be paused and they can be resumed. And the reason this is able to be done is because tasks are more than just a function, right? In the JavaScript models, tasks are a function, and we can model them as just a function because either the function is finished or it's not, right? Like it's very, very simple. But in this model, we have like a thread-like thing, and thread is kind of like an operating system thread. And so tasks have state. They have like a stack, and that's how we can, like when the task is running, it's putting things on its stack, and then we can stop it and come back to it, and the stack is still there. So it can resume what it was doing, right? These are kind of stateful things, and that's how we're able to pause them and resume them. And so Effect's fiber model it doesn't use this cooperative multitasking, it uses this preemptive multitasking model. And so there's these things called fibers, which you might have heard of. And fibers are, you might have also heard of a green thread, right? Like in Go, there's a Go routine. This kind of exists in kind of other concepts. Maybe you've worked with Alexa, there's processes. And so these are a lightweight in-memory thread. So they are a thing, they're an object in memory. And in effect, they actually do have a stack, like they have an actual stack. But they are a thing that exists within memory that represent kind of some computation. And we can have lots of these. We can spawn thousands. They're very, very cheap. They're basically an object with some properties. And so if an effect is a description of a program, a fiber is a running instance of that program. So when we run an effect, we run it in a fiber. And while that effect is running, there's a fiber that represents the running of that effect. And so fibers can be paused, they can be restarted, or they can be awaited to get the result of that effect. Or we can interrupt them. Right? So we have this thing called a fiber. It is running an effect, and it is like a value. It is an object. And we can externally interact with it. And we can stop it, and we can restart it, and we can wait for it to finish. Lots of operations on this thing. And this is how we're able to abstract away sync versus async, right? That was one of the things I said at the very beginning. There's no sync effect, there's no async effect. There are only effects. And the reason this is able to happen is because when we run the fiber, just like how the fiber, everything is synced to the fiber. There is no async. The fiber only runs when it has values. Like if you think about a generator function, when we yield a value, we can kind of operate, our generator function is kind of written as if that value comes back immediately. But it might not come back immediately. But the reason we can work like that is because effect is doing a lot of stuff behind the scenes to basically, if that fiber is waiting on the result that effect will asynchronously resolve, that fiber basically gets paused, and we only restart it when we have the result of the thing that fiber was waiting on. Yes?
Is the whole generator function a single fiber or every yield to a single fiber?
I would say that like the basis of that question has a misunderstanding of fibers, but I'm hoping that I will show you more examples, and that will make sense. Okay. Quickly back to the slides. How is this possible, right? Because like I said, JavaScript's async model is completely different, right? And so I don't know how many of you are familiar with how operating systems work, but in your operating system, like your CPU, basically there's no way to stop kind of an in-process a thing as it's running. Like there has to be something else. And so in an operating system kind of context, there's like a syscall, which is basically yielding to the operating system, or there's a hardware interrupt, which kind of transfer control back to the operating system. And basically in JavaScript, right, there is no way to stop like that while true loop, right? Like no matter how hard we try, that while true loop will never resolve. And so what we need to do is basically split up our program into a bunch of little steps, right? If we split up our program into a bunch of little steps, and then if something like an external thing, we can maybe call it a runtime, that's going to execute each of those steps one by one, well then if we want to stop, we can just not execute the next effect, right? Or the next thing, effect, right? Because this is what effect is actually doing. And so, right, when we have these programs that are made up of effects, they're made up of all these kind of individual operations, right? We have a succeed, and then a map, and then a flat map. And so that's how we're able to stop the computation of something, because we've split up the computations into all these little steps. The effect runtime can, as it's running an effect, just not run the next step and do something else instead. Okay. But again, the runtime isn't magic. So if we call while true within effect, or in this case do this, if we do this, there's nothing effect can do, right? It can only do so much. And so there's this saying in Rust async, which is applicable here, of don't block the executor. If you, and this is really no different than if you have because JavaScript is only single-threaded, if you have an async web server and you do a read file sync, your entire web server is blocked for the duration of that big synchronous call. No matter how hard you try, right? There's only one main thread, and so yeah, just like with normal async, if you have a big long blocking call, there's not much we can do. And so let's see. Here, so right, if we have this big long blocking call within effect.sync, that's going to block the runtime. But again, if we split this up into little steps, where instead of having this big while true loop, if we while true yield effects, that's going to yield 100,000 effects. And so then we have 100,000 opportunities for the effect runtime to come in and say, stop, right? I'm going to do something else. And so we're almost back to the first example now. And the question is, how do we spawn new fibers? And that's where we use effect.fork. And so effect.fork is going to take an effect, and it's going to give you a kind of handle to the fiber. So it's going to spawn a new fiber. It's going to run the effect you give to effect.fork in that fiber, and give you back basically a handle to that fiber. And so we can look at this example. And so let me make sure I commented out up here. So here we're going to call effect.fork on effect.never. And this is basically an effect that will never complete. We'll just always kind of suspend, basically. And so if we run this, we can see we get this fiber if we call fiber.id. Right? A fiber is like a thing. It's a thing. And so a fiber, like I said, it represents the running of an effect. And so it's generic over two parameters, which are the success and error of the effect it's running, right? Because just like how, so the fiber is encoded with the type of the effect inside of it. And so what that means is if we await a fiber, we're going to get back an exit of the same types, right? An exit of the same success value, or the success type, and the same error type, right? And this exit type we've talked about is kind of the outcome of a computation. So anytime a fiber completes, there's an exit value. And so awaiting a fiber, so again, to clarify, we're calling fork on an effect, and that's giving us a fiber that's running that effect. And so when we await the fiber, we get back the result as an exit. If we join the fiber, we get back the result as just the value. And so hopefully that's enough to explain this first example. Because what's happening here is we have this, and actually interestingly, if we get rid of this effect.fork, this while true loop will never be reached. Because what's happening is this effect.repeat is blocking. So when we repeat this, like this schedule.space, this is going to repeat this effect every 250 milliseconds forever. And so when we yield this, it's waiting for it to end, it's waiting for it to end, it's waiting for it to end. And it's never going to end because we've never like told it to, like we could have a schedule that does 250 milliseconds 5 times, or here we've just said repeat forever. And so this, that kind of running that effect kind of creates an operation that does not complete. And so that's the reason this won't end. This will never kind of go through because this entire effect is kind of waiting on this to finish and it's never going to finish. And so if we want to do other things while that's running, we can call effect.fork. And so now we have 2 fibers. We have the main fiber and the fork fiber. And so the main fiber is going to move on, and it's going to do this big while true loop and keep incrementing. And then every so often, the effect runtime is going to stop that main fiber by just saying, hey, you've done enough, right? Like I'm not going to execute your next thing. And it's going to switch to this other fiber and say, what do you have to do? And it says, I need to log every 250 milliseconds, and it's going to do that. So that is how we can have kind of concurrent things happening without sync or async, because the effect runtime is kind of managing this. And so it is, we can have different fibers, and the different fibers are being kind of scheduled by the effect runtime. I know that's a lot. Can I run it? Of course. This was the same as before. I need to get rid of this. And so one thing that I talked about how this is not logging every 250 milliseconds, it's logging every second. Something we can do is instead of doing this while true, we can yield this increment function with effect.forever. And so this is going to repeat something forever. And if we do that, now it's going to repeat every 250 milliseconds. And so there's a couple reasons kind of behind the scenes why that's happening. The next thing I want to talk about, or let's look at this example. So in this example, we're declaring I, and then we're creating this fiber. We're forking a new fiber that's going to log the value of I every 250 milliseconds. And then we're setting I to 100, and that's the end. So when we run this, what do we think is going to happen? Anyone? Is it going to log? OK. This is not going to log anything. And so the reason this doesn't log anything is because of a very key thing of effects concurrency model called structured concurrency. And so in structured concurrency, every fiber has this parent-child relationship. So we have a fiber, and when we spawn a fiber, we spawn it as a child of the current fiber. And there's this important concept that no child can live longer than its parent fiber. And this isn't really important because there's a kind of other mindset where we just have every fiber living in this big global scope. And that's a problem because we can start leaking things, right? Like if you in a program, let's say you call a library function, and it starts a interval, it calls set interval. And it doesn't give you a handle to that interval. There's no way to get that interval. It's like impossible to stop at this point, right? Or maybe there's a way, but basically there's no easy way. And so what's powerful about this is if we kind of call some library effect, we know that any kind of fibers it creates will all be cleaned up when the kind of parent fiber is cleaned up. And so that way we don't really leak fibers. And there are some kind of escape hatches, so you can actually create a fiber that can outlive its parent, but it's kind of a more advanced use case. But by default, all child fibers cannot outlive their parent fiber. And so what's happening here is we have the main fiber, we have the child fiber. And the main fiber ends. It finishes. After we set I to 100, it ends. And so this child fiber, after this ends, it says, hey, I need to kill all the child fibers. And so this never gets a chance to run. And so This is really, really important. And I talk about a couple reasons for why this is so important. And so there's this diagram. I really like this diagram. So this kind of shows how we can kind of create these kind of deeply nested fiber models, but they always clean up, right? We can be assured that there are no fiber leaks because as soon as the parent fiber ends, it's going to interrupt all of its children, all of its children, all of its children. And I also think this is where we talked about interruption. Mike talked about interruption earlier. We can now kind of think about how we're able to interrupt the computation of a fiber, or of an effect. Because if we're executing an effect in a fiber, we can externally interrupt that fiber. And we can basically say, wherever you're at in the execution of that fiber, stop. And that's how it exits. It exits as an interruption. And where the value of doing things like scope is effect will automatically make sure when you interrupt a fiber, if it has finalizers, it's going to run all those finalizers. And it's going to run all those finalizers in a way where they cannot be interrupted. And so that's quite important for having resources that, right, we don't want to leak a resource because that thing got interrupted. If the thing gets interrupted, of course, we want to make sure the resources associated with it gets closed. So I talked about the alternatives. So callbacks are all kind of live in this kind of obscure global scope. There's also, if you've ever worked with Go, you can't get a handle to a Go routine. You just call Go routine and they just live magically. You have no way to inspect them. And so again, we can leak tasks. Also, if a task errors, right? If a set timeout throws or a set interval throws, who's responsible for that error, right? It's unclear. Where in effect, right, when you have this parent-child relationship, you can say, okay, the parent is responsible for all the errors of its children fibers. Same with resources, right? And how do you stop a task from the outside? We can because we have a handle to it. And this is quite similar to memory management. So if you've ever worked in C or C++, there's a whole kind of a bunch of errors you can make around memory management, where you can forget to free memory, you can leak memory, you can free memory too early. And so Rust came in, and Rust said, I'm going to give memory an owner. And memory can only have one owner. And when the owner drops it, that's when we free the memory. And so this is quite similar, where in C or C++, you could do everything properly, and you probably wouldn't run into any issues, but you probably will eventually. And so it's the same with concurrency, right? Like, if we did everything, we might kind of do it right. But here, we can say, OK, this concurrent task has an owner. And when that owner gets interrupted, or it finishes, or it succeeds, whatever happens, that other concurrent task can't leak. And so I talked about some escape hatches. So the main one is this thing called fork daemon. And so this is going to spawn a fiber in the global scope. So that's how you opt out of the kind of parent-child hierarchy. Although you should only do this if you know what you're doing, right? Because you kind of throw out all the guarantees of this kind of relationship if you don't. And so I have some examples here to look at. Actually, most of these are on fiber-to-fiber communication. So does anyone have questions about fibers? So unfortunately, I have not worked with Alexa enough to have a good understanding of what an agent is. But I think effects or fibers can be stateful in that, like, the kind of computations they're running can be stateful. And so this is where we can look at fiber-to-fiber communication. So you can have two fibers and they can talk to each other. So this is very common in Alexa, right? Instead of operating on shared state, we can message pass between these kind of concurrent tasks. And so there's a bunch of really cool ways to do this in effect. So there's this thing called a deferred. And a deferred is basically a promise, but better. And so a deferred has a success type and an error type, just like most things in effect. And one fiber you can wait on a deferred, you can pull a deferred, and then another fiber can resolve the deferred or reject the deferred. And so in this way, you can kind of synchronize fibers, right? You can have 4 fibers waiting on something, and then one other fiber kind of resolves that deferred, and now these can finish. And there's also a queue, and a queue is basically a channel. So we can send to a queue, we can take from the queue, and so these are kind of how we communicate between fibers. And queues are async, but they're async in that the operations on a queue are blocking. And this is where I talked about how we're able to have these blocking things, but still be async. So when you pull from a queue, if the queue is empty, it's going to block that fiber. But the reason that it can block is because the effect runtime is going to see that it's blocked, and it's basically going to say, well, I know that you're waiting on something that hasn't happened yet, so I'm going to go execute other fibers in the meantime, right? And so that's how we can have these APIs that block the current fiber, but other things can still run. And so queues, like I said, have customizable back pressure. So what that means is if we are sending things into the queue faster than they're being consumed, we can you can set an unbounded queue, so the queue the kind of buffer that's holding all the items that haven't been taken out yet, that can grow indefinitely. We can have a bounded queue that makes when we try to put something onto the queue, that can block if the queue is full. We can also have a sliding queue or a dropping queue, and so if we try to put onto the queue when it's full, it can either drop from the front or drop from the back. There's also this thing called a pub sub, which is a way to publish messages to multiple subscribers. So we can create the pub sub, and we can put messages into the pub sub, and we subscribe from the pub sub. We get a way to pull messages out, and this is like each subscription will get its own instance of every message. Where with a queue, if you have multiple fibers trying to pull off the same queue, well, there's only kind of like for each item in that queue, it can only be pulled off once. But a subscription, every subscription is going to get its own copy of every value that gets put on. And then the other thing, something kind of cool, is the subscriptions have a scope. So that's how they're able to kind of like when you subscribe, the subscription of the pub sub requires a scope. And so when you close the scope, it unsubscribes to the pub sub. So that's a kind of cool use of scope. We have a couple minutes left. I'm going to quickly run through this. I'm actually going to skip this. High-level abstractions. We talked about fibers, super low. What's the stuff you're going to use all the time? Working with fibers directly is not very common. Basically, every combinator that operates on multiple effects has a concurrency option. So in effect.all, which is the most common place you'll see this, you'll see the effect.all concurrency unbounded. And so what this internally is going to do is it's going to spawn a fiber for each effect, and it's going to run each fiber in an effect currently. And if one of them fails, it's going to automatically interrupt the other fibers for you, right? And so this is doing a lot of work under the hood, and you get all the benefits of the structured concurrency, right? Like if we run this, and then the fiber that's running this gets interrupted, all of the fibers that are getting run concurrently in here, they're all going to get interrupted, right? So we get all the benefits of structured concurrency in one line. And then this is something you can't do with promise.all. If you want to run these, let's say, with a maximum concurrency of 2 at a time, you literally just put a number. And now it's only going to spawn 2 fibers, and we're only going to maximally run 2 of these effects that we pass to it concurrently at the time. And so we can see that down here. And this can also be controlled externally. So we can use concurrency inherit, and then somewhere kind of higher up in our program, one sec, we can call effect.withConcurrency, and that's going to set the concurrency limit for effects that use concurrency inherit deeper down. Yes?
Yeah, it's all one node process, right?
Yes, all one node process. So there's a thing called effect.cluster, which I'm pretty sure there's a talk about tomorrow that kind of talks about more than one node process, but this is all happening on one node process, just one thread, just one thread. There are. So that's something we didn't get to. If you check out, there's a slide. So there's this thing called effect.platform, and this is a good thing to know about. An effect.platform is a package that describes platform-independent interfaces for common platform things. And so there's a terminal service, there's a file system service, there's a worker service, there's tons of worker abstractions. And then we can import, there's like a platform node, a platform button, a platform browser, right? And we can provide platform-specific implementations of those services depending on what platform we're using. And so that's a really kind of great example of how to use or a usage of the kind of services is effect.platform. And there are tons of worker abstractions. I would say if you want to look, the best example of that is in the source code in platform, I think platform node or just platform in one of the examples, or in the tests, there's a worker example, and that will show you that. And then the one final thing I want to talk about is that's too much. OK, so yeah, the big thing is all effects that operate on multiple values. So effect.all, effect.zip, there's a bunch of them. Concurrency, either unbounded or inherit or a number, and that's going to allow you to run stuff concurrently. Oh, yes. And but this is the same where we talked about. So this is going to short circuit by default, right? So if one fails, all of them are going to fail. And so actually, like using like this or using like this, you actually you really don't think about fibers, because this is going to operate basically the same way as if you didn't do this, but concurrently. And so you don't have to think about fibers at all doing this, but it is going to have the fibers under the hood. And yeah, any more questions about schedulers? Or not schedulers, fibers. I think we're running out of time. The one last thing I want to talk about is performance. So I'm just going to fly through these. Performance is a big thing. We all want to be performant. Obviously, effect code, it's kind of doing a lot, right? There's this whole runtime, there's a scheduler, there's all these fibers, we're encoding everything in these objects, and so effect has some overhead. It's never going to be as fast as just writing pure JavaScript. But effect is made for application code where the limitation is almost always I/O anyway, right? And so that's where, if you talk to Mike, you would literally say, like, find me when effect is your bottleneck, right? And so effect will likely improve the performance with its powerful concurrency primitives. So the ability to structure concurrency, interruption, and like worker pool abstractions, these are tools that we can use to control concurrency better, and that will have a much bigger impact on the performance of our code. And then finally, if you're writing CPU-bound code, you probably should not use effect. Or you probably shouldn't really be using JavaScript or TypeScript, right? So that's all I got for today. The slides in the GitHub, in the code will all be available on my GitHub. There is a lot for you to go through with those two middle things. I think there's a lot you can learn from, and the exercises in there, there's also more snippets, tons and tons to learn. If you have feedback, I know there's the box over there, but yeah, I wouldn't use that. But if you want to use the feedback box, it's over there. If you want to talk to me on Discord, talk to me on Twitter, feel free. I would love to speak about effect with you. I'd love to teach you more. And then, of course, I'm going to be at the conference tomorrow. So please, please, please come say hi to me. I'd love to talk to you. And I hope you learned a lot. Thank you so much, everyone.